There is a particular sound that finds you in the dark. Soft, at first, then steady. A gentle percussion on the roof above your head, on the window glass beside your pillow. Rain. You've heard this sound 1,000 times before, maybe 10,000. Rain has been the soundtrack to countless nights of your life, falling while you lay safe and warm beneath blankets, your breath slowing, your thoughts beginning to drift. There is something about rain that makes the world feel smaller, softer, more manageable. The walls around you become more than walls, they become shelter. The roof above you isn't just covering space, it is keeping you dry while water falls from the sky. Scientists have studied why rain sounds soothe us. Part of it is the acoustic quality rain creates what is called pink noise, a sound frequency that masks other noises without being jarring or attention-demanding. It fills the silence without creating tension. Your brain can rest against it the way your body rests against a mattress. There is no sudden change, no spike to jolt you alert, just the steady, patient rhythm of water finding earth. But there is more than acoustics at work. Rain sounds carry memory. Perhaps you remember childhood nights, rain on a tent during camping trips, or the particular drumming on the metal roof of a grandparent's house. Rain sounds like safety because it meant staying inside, staying together, staying still. In our evolutionary past, rain meant our ancestors could rest, predators would shelter too, tracks would wash away. The hunting pause. Some deep part of your nervous system still knows this. Tonight, as rain falls somewhere outside your awareness, or as you imagine it falling, there is a question worth wondering about. You've heard this sound so many times, felt comforted by it countless nights, but have you ever truly considered where it comes from? Not the simple answer, from the sky, but the real journey of rain. The strange and beautiful path that every drop takes before it reaches your window. What if I told you that the rain falling tonight has traveled further than you might imagine? That each drop has a history stretching back days or weeks, that it has been other things before being rain, that it will be other things again, that the simple sound of water on glass represents the conclusion of an epic journey through transformation. You don't need to know any of this to fall asleep. Rain will soothe you whether you understand it or not. But there is a particular kind of peace in understanding, a deeper settling that comes when wonder is answered. So tonight, let's follow rain backward. Let's trace one single drop from your window, all the way back to its beginning, and in doing so, discover why the sound that helps you sleep is more remarkable than you ever imagined. Where does rain actually come from? It is the kind of question a child asks, eyes wide, finger pointing at the window. And if you're like most adults, you have an answer ready. Rain comes from clouds. Which is true, of course, but it is also just the beginning. It is like saying bread comes from the bakery, which tells you the last step, but nothing about wheat fields or yeast, or the transformation of ingredients into something entirely new. For most of human history, rain was magic, not metaphorical magic, but actual magic, the work of gods and spirits who decided when to water the earth and when to withhold. Ancient peoples danced for rain, made offerings for rain, built entire religious systems around the hope that the sky would open and the crops would grow. Rain was proof that the gods were pleased, or that they'd been successfully persuaded. Some cultures imagined great beings in the clouds, pouring water from enormous vessels. Others believed rain was the tears of the sky, that heaven itself wept for the earth below. Still others thought rain was stored in celestial lakes or rivers, released through divine gates when the time was right. These weren't ignorant guesses. They were sophisticated attempts to make sense of something genuinely mysterious. Water falling from above without any visible source. How could that not be divine? Even in your own childhood, you probably had theories. Maybe you imagined clouds as giant sponges, soaking up water somehow and then squeezing it back out. Maybe you pictured clouds as balloons that could pop, spilling their contents. These intuitive models aren't so different from what ancient adults believed. Rain truly does seem impossible when you think about it. Water, heavy and liquid, somehow suspended miles above your head, then falling in perfect drops. How? Why doesn't it all fall at once? Why does it fall at all? The true answer, as it turns out, is more beautiful than the myths. There is no God pouring from a vessel, but there is a kind of alchemy. There is no celestial lake, but there is an ocean in the sky, just not one you can see. Rain is transformation, repeated endlessly. Water becoming vapor, becoming droplet, becoming rain, becoming vapor again, around and around for billions of years. The same water, just changing costume, playing different roles in an ancient cycle that predates human consciousness by eons. Tonight, you don't need to believe in rain gods or sky sponges, but you also don't need to reduce rain to pure mechanics, to simple cause and effect. Rain is both physical process and mystery, both explainable and wondrous. You can understand exactly how it works and still feel amazed. In fact, understanding often deepens amazement, because the real story is so much stranger and more intricate than any myth we invented. So let's discover that story together. Let's start with one drop, just one single raindrop, and follow its journey backward through time and space, through transformation and change, until we reach the beginning. Or what seems like the beginning, because with rain, beginnings and endings blur together into one continuous cycle. We're going to take a journey tonight, you and I, not a hurried journey. There is nowhere we need to be, nothing we need to accomplish. Just a slow tracing backward through the life of a single raindrop, following its path in reverse, like rewinding a film, watching how it arrived at your window from the vastness of sky and ocean and air. We'll start where rain ends, at a surface, your window perhaps, or a leaf, or a patch of ground. That moment of arrival, that small percussion of water meeting solid. Then we'll pull back, watching the drop rise in reverse through the air, climbing through wind and temperature layers, back toward the cloud that released it. But we won't stop at the cloud. We'll go further back into the cloud itself, watching our drop become smaller, just one tiny droplet among billions, then smaller still, dissolving into individual molecules of water vapor, invisible in the air. We'll watch how these molecules rose from earth or ocean, how they were lifted by warmth and air currents into the high cold atmosphere. We'll discover what clouds actually are, not white fluff or cotton candy, but something stranger and more specific. We'll learn why they float despite being made of water, why they sometimes produce rain and sometimes don't, why they take the shapes they do. We'll understand the moment before rain, the tipping point when a cloud finally lets go. We'll explore the invisible stage before clouds, when water exists as vapor mixed through the air, riding on thermal currents like an invisible mist. We'll see how sunlight provides the energy that makes the whole cycle work, how heat from a star 93 million miles away lifts water into the sky above your head, and we'll understand the descent, how a drop, once formed, falls through kilometers of air, shaped by wind resistance, possibly passing through freezing layers, definitely encountering millions of specific conditions that affect whether it reaches the ground as rain or something else entirely. Along the way, we'll notice things, the time scales involved, how long each transformation takes, the improbable choreography of molecules and temperature and pressure that must align for rain to exist at all, the deep history of water on this planet, how the rain falling tonight contains molecules that have been rain before, countless times, for billions of years. But here is what matters most. You don't need to remember any of this. You don't need to study or concentrate or worry about retention. This isn't school. This is just wandering together, letting curiosity be its own reward, with no test at the end, no application required. If you fall asleep halfway through, that is perfect. If you drift in and out, catching pieces here and there, that is exactly right. The rain itself doesn't demand your attention. It falls whether you're watching or not, and this story of rain is the same. It will continue whether you're fully awake to hear it or not. So settle deeper into comfort. Let your body find its preferred position. Feel the weight of blankets, the support of pillow. And let's begin at the end, with a single raindrop, sliding down glass. Look closely at a raindrop on a window pane. Not a real one necessarily. You can imagine it just as well. Picture the small dome of water clinging to glass, distorting the view beyond it. The world through a raindrop is strange, bent, magnified in odd ways, colors separated into component hues by the curve of water acting as a tiny lens. Surface tension pulls it into a bulge on the outer surface, but the glass side is flattened where water meets solid. It is almost like a half sphere, a small transparent dome, and it is not still, even hanging motionless. There is microscopic vibration, tiny currents within the drop itself, the individual molecules in constant motion despite the appearance of stillness. This particular drop, the one we're imagining together, has just completed a journey. It fell from somewhere above, from a cloud we can't see now, in darkness or imagination. It fell through air, past buildings or trees, through wind that might have pushed it sideways or updrafts that slowed its descent. It survived the fall intact, didn't shatter into smaller droplets or evaporate in dry air. And now it is here, clinging to your window, visible only because of how it bends and reflects light. Inside this single drop is everything we're going to explore. Its history is written in the arrangement of its molecules, in the trace minerals dissolved within it, in the temperature it holds. If we could read water-like text, this drop would tell us about the cloud it came from, the altitude where that cloud hung, the amount of pollution or pollen in the air, the temperature gradient it fell through. Every drop carries information, though we usually just see water. Watch as this drop begins to slide. Gravity finally overcomes surface tension's grip on the glass. The drop elongates, stretches into a teardrop shape that isn't actually the shape raindrops take while falling, but only the shape drops make when sliding down surfaces. It accelerates slowly at first, then faster, merging with another drop in its path, becoming larger, now moving quickly down the glass, leaving a wet trail behind it. And then it is gone, off the edge of the window, falling the last few inches to the ground or gutter below. But before it disappears, let's freeze this moment. Let's isolate this drop in time and space, hold it suspended in our attention. This will be our drop, the one whose story will follow. Not rain in general, too vast, too abstract, but this one specific drop, this individual traveler who has just completed a remarkable journey and who, unknowingly, is about to begin another. Where did this drop come from? Not just which cloud, but before that. How did it come to be falling past your window on this particular night? What chain of events led to this moment water on glass? You observing it, this intersection of attention and precipitation. To answer that, we need to watch time run backward. We need to see the journey in reverse, from end to beginning, letting the drop rise back up into sky and story. Imagine running a film in reverse. Events happening backward, effects preceding causes, results dissolving into origins. It is strange to watch water leaping from the ground into glasses, people walking backward, smoke descending into chimneys. But it is also clarifying. Playing things backward lets you see connections you miss. When time flows normally, you notice the chain of causes, the dependencies, the sequence that led to each moment. So let's do that with our raindrop. Let's watch its journey in reverse, like rewinding a recording, seeing where it came from by tracing backward from where it is now. First, the drop rises from your window, water overcoming gravity, floating upward past the building or house, past rooflines and treetops. It is alone, this drop, a tiny sphere of water ascending through air. Around it, other drops are also rising, hundreds of them, thousands all the rain from this shower reversing its fall, climbing back toward the source. Up and up the drop goes, shrinking slightly as it rises. The air gets cooler with altitude, but also drier. Some of the drop's molecules evaporate even as it climbs, so by the time it reaches the cloud layer, it is slightly smaller than when it fell. But it is still recognizable as a drop, still cohesive, still a distinct entity. Now we're approaching the cloud, a gray mass of suspended water hanging in the lower atmosphere. Our drop rises into this grayness and immediately becomes difficult to track. There are trillions of other droplets here, all clustered together, making the cloud visible. Our drop merges into this collective, becoming indistinguishable. But if we could somehow follow its molecules specifically, we'd see it breaking apart, splitting into the smaller cloud droplets it formed from. These cloud droplets continue rising, but now they're shrinking, evaporating into vapor as they ascend through the cloud, and beyond it. The distinct droplet identity dissolves entirely. Now we're following water molecules, individual 3-atom arrangements of hydrogen and oxygen, as they spread through the air in gaseous form, invisible, mixed with nitrogen and oxygen, and all the other atmospheric gases. These molecules continue to drift, carried by air currents, moving both upward and sideways, spreading across the sky. They're warm now, having absorbed heat that allows them to remain gaseous instead of condensing. And they keep drifting backward through time, descending in altitude now, moving from high cold air down toward warmer layers near the surface. Finally, our molecules approach the ground, or more likely the ocean. The majority of Earth's surface is water, so the majority of rain begins there. Backward moving, our vapor molecules descend to the ocean surface and suddenly condense, becoming liquid again, joining the vast collective of the sea. They've come home, in a sense. This is where rain begins, not in clouds, but in oceans and lakes and rivers, in water that exists before it rises. The cycle is complete in reverse, from window to cloud to vapor to ocean. Now we can tell the story forward, in proper time, following this water on its journey to become rain. And that journey begins with something you've seen countless times, but perhaps never really noticed: water disappearing into thin air. Clouds are temporary. This is worth remembering. They look solid and permanent when you see them hanging in the sky, but they're not. They're constantly forming and dissolving, constantly changing shape and density, constantly being refreshed by new water vapor and losing old droplets to evaporation or rain. A cloud is more like a fountain than a sculpture, a continuous flow that appears static but is actually in constant flux. The cloud that held your raindrop before it fell looked like it had been there for hours. Perhaps it had. Perhaps it was part of a large grey cloud deck that stretched across the sky. One of those overcast days where you can't see where one cloud ends and another begins. Or perhaps it was a darker, more defined cloud, hanging low with visible ragged edges where rain was already falling in curtains from other parts of the same cloud. This cloud had weight. Not metaphorical weight, actual weight. A small cumulus cloud, the puffy white kind you see on pleasant days, weighs about as much as 100 elephants. That is about 1,000,000 pounds of water, suspended in air. The larger storm clouds, the ones that bring sustained rain, can contain billions of pounds of water, all of it hanging above your head, invisible architecture of droplets, so small they float. Your raindrop existed in this cloud, as a member of a vast community. Trillions of other droplets surrounded it, none of them touching, yet all of them influencing each other through their collective presence. The cloud was grey from below, grey because of how densely packed these droplets were, how much light they absorbed or scattered. From above, from the perspective of an airplane passenger looking down, this same cloud probably appeared white, even brilliant, reflecting sunlight from its upper surface, while rain fell from its dark underside. Inside the cloud, things were turbulent. Air currents moved through the cloud constantly, updrafts and downdrafts, creating invisible rivers of motion. Droplets rode these currents, sometimes rising, sometimes falling, colliding with other droplets occasionally, growing slowly through these collisions. The cloud was cold, not freezing, but chilly, perhaps 40 or 50 degrees Fahrenheit, cool enough that being inside it would feel like being in a walk-in refrigerator, damp and raw. Your particular droplet had been in this cloud for maybe 15 or 20 minutes before it fell. That is typical. Droplets don't spend long in clouds. They form, they grow, they fall. The cloud itself might persist for hours, but any individual droplet is transient, just passing through this temporary architecture of suspended water. During those minutes, your droplet collided with dozens of others, grew slightly from each collision, became heavy enough to begin sinking through the cloud instead of being held aloft by updrafts. And then the fall began, the moment of release, the droplet sinking out of the cloud's bottom, emerging into clear air below, beginning its descent to Earth. The cloud remained behind, still holding trillions of other droplets, still dark and heavy and full. But your drop was now separate, individual, falling alone through empty air toward the ground below. If you could shrink yourself down and float inside a cloud, it wouldn't be anything like swimming through water. You wouldn't be wet, at least not immediately. You'd be surrounded by a mist so fine it is almost not there. Tiny droplets suspended in air, spaced far enough apart that you'd mostly be floating through emptiness, just with reduced visibility. It would be like standing in the world's thickest fog, where you can barely see your hand in front of your face. Except you'd be breathing normally because there is plenty of air between the droplets. Each droplet in a cloud is incredibly small. They range from about 10 to 20 micrometers in diameter, a micrometer being 1/1,000,000th of a meter. To put that in perspective, a human hair is about 50 to 70 micrometers thick. A cloud droplet is 5 to 7 times smaller than the width of your hair. It is barely there. You could fit several hundred cloud droplets side by side across the period at the end of this sentence. Because they're so small, these droplets have almost no weight. Technically, they do weigh something. Water is water, whether in a drop the size of a pea or a droplet the size of a bacterium. But when something is this small, air resistance becomes proportionally enormous. The droplet's tiny mass can't overcome the friction of air molecules surrounding it. So it floats, drifts, hangs suspended. It falls, but so slowly, maybe 1 centimeter per second, that the slightest updraft carries it back upward. It is essentially weightless in practical terms. This is why clouds don't immediately rain. They're full of water, yes, but that water exists in pieces too small to fall. A cloud is a collection of droplets that individually cannot fall, but collectively create the visible mass we see from the ground. It is a paradox, something heavy that can't fall, because it is divided into pieces too small to fall, like trying to drop a handful of flour through air. The individual grains are so light they just drift, floating on air currents, taking minutes to settle even from waist height. And there are so many of these droplets. A single cubic meter of cloud, about the size of a large refrigerator, might contain 1 billion droplets. Spread them out, and they only add up to about 1 gram of water, about the weight of a dollar bill. But compress 100 such cubic meters, and you've got water equivalent to a large bucket, all divided into trillions of floating particles. Some clouds contain ice crystals instead of liquid droplets, or a mixture of both. High cold clouds are entirely ice-tiny 6-sided crystals that glitter if you're close enough to see them individually. Mixed phase clouds, the ones at medium altitudes, have supercooled water droplets that haven't frozen yet despite being below freezing temperature alongside ice crystals. These mixed clouds can produce particularly heavy rain when the ice crystals grow large enough to fall, because they collect the supercooled droplets as they descend. But the basic principle remains. Clouds are air filled with tiny particles of water or ice, particles so small they drift instead of fall, creating that visible mass of white or gray we recognize from the ground. The question of why clouds float seems paradoxical at first. Water is heavy. It is denser than air, substantially so. A gallon of water weighs over 8 pounds. The ocean lies at the bottom of the atmosphere because water sinks through air. So how can millions of gallons of water hang suspended thousands of feet above the ground, not falling, just floating there like it is forgotten about gravity? The answer lies in division and motion. Take any amount of water, say, a gallon, and divide it into pieces small enough, and those pieces will float. Not because they're lighter than air, but because air resistance overpowers their weight. A cloud droplet falls about 1 centimeter per second, which sounds like falling, except that air is constantly moving. Updrafts within and beneath clouds rise at 10, 20, even 50 centimeters per second. So while individual droplets do fall relative to the air around them, the air itself is rising faster than they're falling. The droplets are caught in an upward wind, like feathers in the updraft from a heat event. The air rises for specific reasons. Sunlight heats the ground, and ground heats the air directly above it. Warm air is less dense than cold air. The molecules move faster, spread further apart, make the air lighter per unit volume. This lighter warm air rises, pushed upward by denser cool air sinking around it. It is the same principle that makes hot air balloons float. The air doesn't want to rise. It is forced upward by heavier air displacing it. As this warm air rises, it carries water vapor with it. The vapor is mixed into the air invisible, just individual molecules scattered among the nitrogen and oxygen and other atmospheric gases. This mixture of air and vapor continues rising until it reaches an altitude where temperature drops below a critical point, the dew point where water vapor begins condensing into liquid droplets. Now you have droplets suspended in rising air. They drift slowly downward through the air around them, but the air itself is climbing faster than they're falling. The result, the droplets gain altitude even while falling relative to their local air. It is like walking down an escalator that is going up faster than you're walking down. You end up rising despite moving downward. Eventually, the air stops rising. It reaches an altitude where it is no longer warmer and lighter than surrounding air, where the lift stops. Now the droplets truly float, drifting in relatively still air, falling very slowly, neither rising nor sinking significantly. Or the droplets reach the edges of the updraft zone and begin descending as the air circulates down around the cloud's periphery. But as long as updrafts persist, the cloud persists. Droplets may cycle through the cloud, rising and falling within it, but the cloud as a whole remains suspended. New moisture constantly enters from below as vapor, condenses into droplets, eventually leaves as rain or evaporates back into vapor. The cloud is not a thing but a process, not an object but an event that looks like an object. It is a visible manifestation of air rising and cooling and releasing its invisible cargo of water. There is a tipping point, a threshold, a moment when a cloud transitions from containing water to releasing it. This moment isn't dramatic. There is no sound, no visible change from outside. But inside the cloud, something shifts. Droplets that have been drifting and floating begin to fall in earnest. Several things can trigger this moment. Most commonly, droplets have been colliding and merging for long enough that some have grown large enough to fall faster than updrafts can lift them. These larger drops descend through the cloud, colliding with smaller droplets in their path, growing larger still, accelerating. It is a feedback loop. The bigger a droplet gets, the faster it falls. The more droplets it collides with, the bigger it gets. Once a droplet crosses a certain size threshold, its growth becomes rapid and its fall becomes inevitable. Another trigger is ice formation. In cold clouds or the upper parts of mixed clouds, ice crystals form. These crystals have a special property. They can grow by stealing water vapor from surrounding liquid droplets. This happens because of vapor pressure differences. Water vapor is slightly more likely to condense onto ice than onto liquid water at the same temperature. So ice crystals grow at the expense of nearby droplets, getting larger while droplets shrink or evaporate entirely. The crystals become heavy enough to fall, collecting liquid droplets as they descend, sometimes melting into rain before reaching the ground. The moment before rain, the cloud has reached saturation. It is holding as much water as it can in droplet form. The delicate balance between water entering the cloud as vapor and water falling from the cloud as rain is about to tip toward falling. Inside the cloud, billions of droplets have grown to the critical size. The cloud has become heavy in a new way, not just full but overflowing, like a sponge that has absorbed all it can and now releases water with the slightest pressure. From the ground you might see the cloud's base become ragged, with dark streaks or a fuzzy edge, where rain is beginning to fall but evaporating before reaching the ground. This is called virga rain that never lands, that dissolves back into air during its descent. As the rain intensifies, the virga reaches lower, evaporating less, until finally the rain survives all the way to the surface. The cloud doesn't empty all at once. Rain falls from some parts, while other parts continue holding their droplets. The cloud might rain steadily for hours, constantly replenished by new moisture rising from below, constantly losing drops from its base. It is a dynamic balance, inflow and outflow, the cloud maintaining itself even while raining. But for any individual droplet that has grown large enough, the moment has arrived. The floating phase is over. Gravity takes hold. The long fall begins. From cloud base to ground, through kilometers of air, the journey that transforms a cloud droplet into what we recognize as rain, a falling drop that makes sound when it hits surfaces, that we can feel on our skin, that we call rain, and not mist or fog. Rain has personalities, and these personalities are determined by the clouds that create them. A summer thunderstorm doesn't rain the same way as a winter drizzle. The difference isn't just intensity, it is character, feel, the entire sensory experience. And these differences trace back to the type of cloud doing the raining. Nimbus stratus clouds bring the steady, gray, all-day rain that makes you want to stay in bed. These are thick, layered clouds that cover the entire sky like a gray blanket, blocking the sun completely, creating that diffuse, shadowless light that feels like neither day nor night. The rain from nimbus stratus is patient, persistent, medium-sized drops falling continuously for hours, sometimes days. It is the rain that cancels outdoor plans, that creates the rhythmic drumming on roofs, that leaves gutters overflowing and worms crossing sidewalks. This is dependable rain, boring rain, the rain that feels most like what rain is supposed to be. Cumulonimbus clouds, by contrast, are drama. These are the towering thunderheads that can reach 7 or 8 miles high, their tops flattening against the stratosphere in that characteristic anvil shape. The rain from cumulonimbus comes in bursts, often beginning suddenly and intensely. The drops are larger, sometimes huge, almost painful when they hit your skin or your car windshield. This rain is loud, violent, exhilarating. It floods streets in minutes, overwhelms storm drains, creates instant rivers in gutters. But it usually doesn't last long. The storm passes. The rain stops as suddenly as it started. and sunlight breaks through in that particular golden quality that only follows summer downpours. Stratus clouds produce drizzle more than rain. These are low, grey, formless clouds that create overcast skies without much depth or drama. The drops they release are tiny, barely larger than cloud droplets, falling in that mist-like way that seems to hang in the air more than fall through it. You can walk through drizzle and barely get wet, though stay out long enough and you'll be soaked. It is sneaky rain, subtle rain, the rain that collects on glasses and hair, that makes everything damp without obvious wetness. Then there are stratocumulus clouds, those lumpy grey sheets that create a mottled sky. They produce intermittent light rain or drizzle, unpredictable, starting and stopping. And altocumulus clouds at mid-levels that occasionally rain, creating those strange moments when rain falls from a cloud that doesn't look particularly dark or threatening, catching you by surprise. Each cloud type creates rain from its own structure and dynamics. The thick vertical development of cumulonimbus allows for large drops and ice processes. The shallow horizontal spread of stratus only permits small droplets. The layered stability of nimbostratus enables long-lasting steady precipitation. The cloud is the factory, and its architecture determines what kind of rain it can manufacture. When rain falls on your window tonight, it carries the signature of the cloud that made it. Heavy drops from tall clouds, fine mist from low ones, steady rhythm from layered clouds. Each has traveled its own specific path, formed in its own specific way, falling with its own particular character. So now we understand clouds, what they are, how they float, why they rain, how they differ. We've watched our raindrop existing in its cloud, suspended among trillions of others, slowly growing heavy enough to fall. We've seen the moment of release, the beginning of its descent. But this is still not the beginning of the story. The cloud was temporary, remember. It formed from something else, something that existed before the cloud appeared. Before there was a visible cloud full of droplets, there was invisible air full of vapor. Before our raindrop could exist in any form, the water molecules that compose it had to rise into the atmosphere as an invisible gas mixed into the air, undetectable to the eye. This is the stage before clouds, the invisible phase of the water cycle. It is harder to visualize because there is nothing to see. Water vapor is transparent. You can't point at it in the sky. You can't photograph it. You only know it is there by its effects: humidity, the sticky feeling of muggy air, the condensation on cold glasses, the fog of your breath in winter. But this invisible water is crucial. It is the majority of water in the atmosphere at any given moment. Only a small fraction has condensed into visible clouds and rain. Most of it is still in vapor form, riding air currents, absorbing and releasing heat, waiting for the conditions that will transform it into something visible. So, let's go further back. Let's follow our raindrop through its invisible phase, back before it was a droplet in a cloud, back when it was molecules of vapor rising from the surface, scattered and unseen. This is the hidden journey that precedes all visible weather. This is where rain truly begins, with water disappearing into air, becoming invisible, starting the long climb toward the sky where clouds will eventually form. You've seen water disappear, everyone has. A puddle on the sidewalk after morning rain, gone by afternoon. Laundry hung outside, wet when you pinned it up, dry hours later. Your breath visible in winter cold, then vanishing into air. The surface of a lake on a summer morning, steaming as the sun rises, the water seemingly becoming smoke and drifting away. We call this evaporation, and the word itself suggests something ghostly, water vanishing, passing away, leaving no trace. But water doesn't actually vanish. It just changes form so completely that we can no longer see it. The water from the puddle is still there, still in the air around where the puddle was. The water from the laundry is still in the atmosphere, just mixed into it, invisible, scattered among the other gases that make up air. This transformation happens constantly, everywhere there is water exposed to air. Ocean surfaces, river surfaces, soil moisture, plant leaves, even your skin, all releasing water molecules into the air, one molecule at a time, billions per second, creating an invisible flux of water from liquid form into gaseous form. The strange thing about evaporation is how quiet it is. There is no sound, no visible change at the moment it happens. Unlike boiling, which is dramatic and obvious, evaporation happens at any temperature, even in winter, even from ice. It is patient and persistent. You can watch a puddle for an hour and not see it shrink, but check back the next day and it is gone. The process is too slow for the eye to track, but too constant to be stopped. What is actually happening at the molecular level is escape. Water molecules in liquid form are constantly moving, vibrating, jostling each other. They're held together by hydrogen bonds, weak attractions between the hydrogen atoms of one molecule and the oxygen atoms of nearby molecules. These bonds create surface tension, the skin-like quality of water surfaces. But at any moment, some molecules near the surface are moving fast enough to break these bonds and leap into the air above. They escape the liquid and become part of the gaseous atmosphere. Once in the air, these molecules are free. They're no longer constrained by other water molecules, no longer part of a liquid mass. They drift with air currents, they travel, they spread out. They're invisible now. Single molecules don't reflect enough light to see. They've gone from being part of something visible to being part of something invisible. From liquid water you can touch and see, to water vapor you can't detect except through its effects. This is how rain begins, with water leaving surfaces, becoming airbound, starting the upward journey. Every raindrop that falls was once vapor that rose, before it condensed in clouds, before it formed droplets, before it fell, it evaporated. It left the surface as individual molecules, invisible escapees from ocean or lake or river, beginning the long transformation that would eventually bring them back to Earth as rain. And it all starts with sunlight. Picture a single water molecule at the ocean surface. It is one among countless others, all packed together in liquid form, constantly moving, vibrating with thermal energy. This molecule is made of 3 atoms, 2 hydrogen, 1 oxygen, arranged in a bench shape like a Mickey Mouse head. It is bonded to neighboring molecules through hydrogen bonds, those weak electrical attractions that give water its liquid properties. The molecule is vibrating. All molecules vibrate. It is a function of temperature. The warmer something is, the faster its molecules move. At the ocean surface on a sunny day, molecules are moving quite fast, jostling each other constantly, stretching and breaking and reforming hydrogen bonds hundreds of times per second. Our molecule happens to be near the surface, in the top layer where water meets air. Above it is atmosphere, nitrogen, oxygen, argon, carbon dioxide, and already some water vapor from molecules that escaped earlier. Below are billions more water molecules, stretching down to the ocean floor. Our molecule is bouncing against its neighbors, absorbing energy from sunlight that is warming the water, moving faster with each quantum of absorbed heat. Then, in one particular collision with a neighboring molecule, something changes. Our molecule receives just enough kinetic energy to overcome the hydrogen bonds, holding it to the liquid surface. It breaks free. In an instant measured in microseconds, it passes from liquid phase to gas phase, from being part of the ocean to being part of the air. The molecule shoots upward, not far, just a tiny distance measured in nanometers, but far enough to enter the atmospheric realm. Immediately it is moving differently. In liquid form, it was constrained, always surrounded by and bonded to other water molecules. Now it is free, floating, traveling much further between collisions, bouncing off nitrogen and oxygen molecules instead of other water molecules. It is become vapor. This molecule is now significantly less dense than it was. In liquid form, packed tightly with other water molecules, it occupied very little space. In vapor form, it spreads out, traveling freely, occupying space determined by the pressure and temperature of the surrounding air, rather than by proximity to other water molecules. 1 gram of liquid water occupies 1 cubic centimeter. That same gram of water vapor at sea level on a warm day occupies about 1,700 cubic centimeters, more than 1,000 times the volume. The molecule continues moving upward, carried by thermal motion and by rising air currents. It collides with other air molecules millions of times per second, bouncing randomly, but with a general upward trend because warm air near the surface is rising. The molecule is now part of humidity, that invisible presence of water in air that we feel on muggy days, but never see. This escape happened to billions of molecules in the same instant, and it continues happening, constantly, wherever liquid water is exposed to air and sunlight. The ocean surface is always evaporating, always releasing molecules into the atmosphere, always beginning the process that will eventually create clouds and rain. Our particular molecule is now rising, invisible, climbing through the lowest layers of the atmosphere on its journey toward becoming a raindrop. The sun is responsible for almost all movement of water on Earth. Not just daylight, not just warmth for comfort, but the actual engine of the water cycle. Every drop of rain that falls owes its journey to solar energy. The sun lifts water into the sky, against gravity, without ever touching it directly. It does this with light with radiation traveling 93 million miles through space to warm Earth's surface and make water molecules energetic enough to escape. Light carries energy. This is easy to forget because light seems insubstantial, but every photon that strikes a surface transfers a tiny amount of energy to whatever it hits. Sunlight warms your skin because photons are depositing energy into your skin cells. Sunlight warms the ocean surface because photons are depositing energy into water molecules. That warmth, that increased molecular motion, is what allows evaporation to happen. Without the sun, Earth would be frozen. All water would be ice, locked solid, with no evaporation, no clouds, no rain. The water cycle would stop completely. Rain exists because the sun exists, because it pours energy onto Earth's surface continuously, because that energy gets converted into molecular motion, and because that motion allows liquid water to become vapor. The sun doesn't just provide heat, it provides the differential that drives circulation. The equator receives more direct sunlight than the poles. This creates temperature gradients, which create pressure gradients, which create wind. Air moves from high pressure to low pressure, carrying water vapor with it. The whole atmospheric circulation trade winds, jet streams, storm tracks, is powered by uneven solar heating. Rain falls in some places more than others, because the sun heats some places more than others. Even the clouds themselves exist because of solar warmth. The rising air that creates clouds is air heated by the sun-warmed surface. The towering thunderheads of summer form because intense solar heating creates powerful updrafts. Without solar energy constantly adding heat to the lower atmosphere, air would be too stable to rise, too cold to hold much vapor. There would be no clouds. This has been true for billions of years. As long as the sun has been shining on Earth, roughly 4.5 billion years, water has been evaporating and condensing and falling and evaporating again, the same water cycling repeatedly, powered by the same solar energy, pouring down continuously. The sun is ancient and will continue for billions of years more, and as long as it does, water will cycle. So when you hear rain, you're hearing the sound of captured sunlight. The rain falling on your window absorbed solar energy when it was ocean water, used that energy to evaporate and rise, and form clouds, and now releases some of that energy as kinetic energy, the energy of motion. Rain is solar energy transformed, translated through water's journey, arriving at your window as percussion and rhythm. The sun doesn't know it is making rain. It just shines continuously, pouring energy onto a planet where water happens to exist in abundance. And that combination, sunlight plus liquid water plus an atmosphere, creates weather, creates clouds and rain, and all the complexity of Earth's hydrological cycle. On humid days, you know water vapor is there even though you can see it. You feel it. The air feels thick, substantial, almost liquid itself. Breathing feels like inhaling moisture. Your skin doesn't dry properly. Sweat doesn't evaporate as readily because the air is already saturated with water molecules. Everything feels damp, heavy, oppressive in a way that has nothing to do with temperature alone. This is humidity, the presence of water vapor in air. It is invisible water, chemically identical to the liquid water in puddles and oceans, just in gaseous form, scattered throughout the atmosphere. The molecules are so spread out, so diluted among the other atmospheric gases, that they don't create any visible effect. But they breathe air billions per cubic centimeter, waiting for the right conditions to condense back into liquid. Meteorologists measure humidity in several ways. Relative humidity is the most common. It is the percentage of water vapor currently in the air compared to the maximum amount the air could hold at that temperature. When the weather report says 80% humidity, it means the air is holding 80% of the water vapor it is capable of holding. At 100% humidity, the air is saturated, unable to hold more vapor without some condensing into liquid. This is when fog forms, when dew appears on grass, when condensation covers windows. Warmer air can hold more water vapor than cold air. This is crucial for understanding clouds and rain. The maximum capacity for vapor increases dramatically with temperature. Air at 86 degrees Fahrenheit can hold twice as much vapor as air at 68 degrees Fahrenheit. This is why tropical regions are so humid. The warm air can dissolve more water vapor, so more evaporates into it, creating that muggy heaviness. When humid air rises and cools, its capacity to hold vapor decreases. The vapor doesn't disappear, the molecules are still there, but now there is too much vapor for the temperature. The air becomes supersaturated. This is when condensation begins, when water vapor starts to condense into liquid droplets. This is how clouds form, by cooling humid air until it can't hold all its vapor anymore. Humidity varies enormously by location and time. Desert air might have 10% relative humidity, very dry, barely any vapor. Tropical air near the ocean might be at 90%, nearly saturated, heavy with moisture. The same location can vary from morning to afternoon. Dew soaking the grass at dawn, air drying out by noon as temperature rises and relative humidity drops. The water vapor in humid air is the raw material for rain. Every rain cloud forms from humid air that rose, cooled, and condensed. No humidity means no clouds. No clouds means no rain. Deserts are dry not just because it rarely rains there, but because there is not much water vapor to form rain clouds in the first place. The driest places on Earth, Antarctica, its interior, the Atacama Desert, have air so dry that there is almost no vapor to work with, even when conditions would otherwise allow clouds. So humidity is invisible potential rain. It is water waiting to become visible, waiting for the right conditions to transform back into liquid and fall. Water vapor doesn't rise on its own. It rises because air rises, and water vapor is mixed into that air. Where air goes, vapor goes. They are inseparable, or at least they separate only when conditions force vapor to condense back into liquid. Until that moment, vapor is just another constituent of atmospheric gas, carried wherever air currents take it, and air rises constantly. All around you, right now, there are columns of air climbing upward, carrying vapor with them. This is happening over sun, heated pavement, over dark soil, over every surface that is absorbing more solar energy than its surroundings. The heated surface warms the air directly above it. That warmer air becomes lighter, less dense than the cooler air surrounding it, and lighter air rises, displaced upward by heavier air sinking around it. You can see this sometimes. Heat shimmer over hot asphalt is the distortion of light passing through rising warm air. The wavering effect of heat above a candle flame is rising air made visible through its optical effects. Smoke rises not because smoke is lighter than air, it is actually heavier, but because it is carried upward by the hot air from the fire. These rising columns of warm air are called thermals. Birds use them, soaring without flapping by circling within thermals, gaining altitude effortlessly as the thermal lifts them. Glider pilots seek them out, riding invisible elevators in the sky. And water vapor rides them too, climbing from surface level toward higher altitudes, toward the colder air where condensation might eventually occur. As vapor-laden air rises, several things happen. First, pressure decreases with altitude. There is less atmosphere above pressing down, so air expands. This expansion causes cooling, even though no heat is being lost. It is an adiabatic process, temperature dropping because of expansion, not because of heat transfer. The cooling is substantial, about 5.5 degrees Fahrenheit for every 1,000 feet of altitude gained, as long as no condensation is occurring. Second, the air mixes with surrounding air as it rises. Turbulent eddies blend the rising warm air with adjacent cooler air, creating a gradual transition rather than sharp boundaries. The vapor mixes too, spreading from concentrated pockets into broader distributions. Third, if the air rises high enough and cools enough, it reaches the dew point, the temperature at which it can no longer hold all its water vapor in gaseous form. At this point, the invisible becomes visible. Condensation begins. Cloud formation starts. But until that threshold is reached, the vapor remains invisible, just riding the rising air currents. climbing higher and higher into the atmosphere. Some vapor might rise thousands of feet before encountering conditions cold enough to condense. Some might rise all the way to the upper troposphere, 7 or 8 miles up, before finally forming ice crystals in high cirrus clouds. The rising is patient. It is not dramatic or fast. Typical updrafts rise at a few meters per second, taking many minutes to carry vapor from surface to cloud, forming altitude. But it is constant. Somewhere above every warm surface, air is rising and vapor is rising with it, beginning the journey that might eventually end as rain. The atmosphere is layered by temperature, and this layering is crucial for cloud formation. At ground level, temperature varies by location and time of day, but once you start climbing in altitude, patterns become more predictable. In general, temperature drops as you go higher. This seems obvious. Mountains are colder than valleys. Jets cruise at altitudes where outside temperatures are far below freezing, but the reasons for this are worth understanding. The atmosphere is warmed from below, not from above. Sunlight passes through air without heating it much directly. Instead, sunlight heats the ground, and the ground heats the air, touching it through conduction and radiation. This means the warmest air is at the surface. As you move away from that heat source, temperature drops. On average, temperature decreases about 3.5 to 6.5 degrees Fahrenheit for every 1,000 feet you climb. This is called the lapse rate, and it varies depending on humidity and other factors. But the principle holds: up is colder. If it is 70 degrees at sea level, it might be 50 degrees at 5,000 feet, 30 degrees at 10,000 feet, near zero at 20,000 feet. This gradient creates the conditions necessary for clouds. Imagine rising with a parcel of humid air, an imaginary box of air molecules and water vapor molecules mixed together, being carried upward by thermals. At ground level, this air might be 75 degrees and 70% relative humidity. It feels warm and slightly sticky. The water vapor is completely invisible, just mixed into the air. As this parcel rises, it expands because pressure decreases with altitude. This expansion requires energy, which comes from the air's own heat, so the air cools as it expands. At 2,000 feet, the parcel might have cooled to 65 degrees. At 4,000 feet, maybe 55 degrees. The cooling is mechanical, automatic, unavoidable as long as the air keeps rising and expanding. But here is the crucial part. While the temperature is dropping, the actual amount of water vapor in the parcel isn't changing. The number of water molecules remains the same. What changes is the air's capacity to hold that vapor. Cooler air has less capacity, so even though the parcel started at 70% relative humidity, by the time it reaches 4,000 feet and has cooled to 55 degrees, the relative humidity might be 90%. Same amount of vapor, but colder air, so higher relative humidity. Eventually, if the air keeps rising and cooling, it reaches a temperature where it is holding exactly 100% of the water vapor it is capable of holding. This is the dew point, the temperature at which air becomes saturated. Any further cooling, even by a single degree, and the air is supersaturated. What gives is that the excess vapor condenses into liquid. Water molecules begin clustering together, forming tiny droplets. The invisible becomes visible. A cloud begins to form. This happens at a specific altitude called the lifting condensation level. It is the height where rising air has cooled enough to reach its dew point. On some days, this might be at 3,000 feet. On drier days, it might be 8,000 feet or higher. On very humid days, it could be just 1,000 feet above ground, which is why clouds sometimes seem to nearly touch the ground. The lifting condensation level is where the invisible journey becomes visible. It is the boundary between vapor and cloud, between clear air and condensation, and it is where our raindrop-cess journey takes a crucial turn, from gas to liquid, from scattered molecules to cohesive droplet, from invisible to visible. The easiest way to understand condensation is to think about your breath on a cold day. You exhale, and suddenly there is a visible cloud in front of your face. Where did that cloud come from? Your breath, the air from your lungs, is warm and humid, about 98 degrees and nearly 100% relative humidity. It contains significant water vapor from your lungs and respiratory system. When that warm, humid breath hits cold winter air, it cools instantly. The water vapor it contains suddenly encounters an environment too cold to keep it in vapor form. In a fraction of a second, the vapor condenses into tiny liquid droplets, creating a visible mist. You are watching condensation happen in real time, right in front of your face. This is exactly what happens in the sky when clouds form, just at a larger scale. Warm, humid air rises into colder regions of the atmosphere. When it cools past its dew point, water vapor condenses into droplets. The cloud is essentially a massive version of winter breath, water vapor made visible through condensation. The droplets in your breath cloud are similar in size to droplets in atmospheric clouds, 10 to 20 micrometers, small enough to float on air currents rather than fall immediately. If you could zoom in on your breath mist, you'd see trillions of tiny water spheres suspended in air, reflecting light, making the invisible water suddenly visible. This analogy helps clarify several things about atmospheric clouds. First, it shows that condensation requires temperature change, not just cold. Your breath is visible on winter days but not summer days, even though the breath itself is the same temperature in both cases. The difference is whether the ambient air is cold enough to cause condensation. Similarly, atmospheric clouds form when rising air cools below its dew point, regardless of what that absolute temperature is. In Arctic regions, they might not form until temperatures are well below freezing. Second, the breath analogy demonstrates that condensation happens quickly when conditions are right. The moment your breath hits cold air, it condenses. There is no delay, no gradual transition. Similarly, when rising air reaches its condensation level in the atmosphere, clouds can form within minutes. One moment there is clear sky. The next moment there is visible cloud. The vapor was always there, condensation just made it visible. Third, you'll notice that breath clouds don't last long. They quickly dissipate, becoming invisible again as the droplets evaporate back into vapor. The same can happen with atmospheric clouds. If they drift into drier air or if temperature rises, the droplets can evaporate, and the cloud disappears. Clouds are only visible when conditions maintain condensation. Change the conditions slightly, and clouds can vanish as quickly as they formed. There is one key difference between breath clouds and atmospheric clouds: duration. Your breath cloud exists for a few seconds before dispersing and evaporating. Atmospheric clouds can persist for hours or days because they are being continuously fed with new humid air rising from below. As long as updrafts keep bringing moisture to the condensation level, the cloud persists, even though individual droplets might evaporate and be replaced by new ones constantly. But the fundamental physics is identical. Warm, humid air encounters cold. Vapor condenses into droplets. Invisible water becomes visible. Whether it is your breath on a winter morning or a thunderhead building on a summer afternoon, the process is the same. Condensation is the transformation that turns humid air into visible cloud, that makes water vapor apparent to the eye, that begins the process of turning scattered molecules into drops large enough to eventually fall as rain. Here is a strange fact. Pure air cannot form clouds, even if you cool humid air far below its dew point, even if it is supersaturated with water vapor. Droplets won't form unless there is something for the water to condense onto. Water vapor needs a surface to collect on, a nucleation site where molecules can begin clustering together. In perfectly clean air with no particles, water vapor would remain vapor even when it is supposed to condense. Fortunately, real atmospheric air is never perfectly clean. It is full of tiny particles, dust, pollen, sea salt crystals, particles of pollution, microscopic fragments of everything. These particles are called condensation nuclei, and they are essential for cloud formation. Water vapor condenses onto these specks, using them as foundation for droplet formation. The particles are incredibly small, mostly between 0.1 and 1 micrometer in diameter, much smaller than cloud droplets, but large enough to provide a surface for water molecules to cling to. They are everywhere in the atmosphere, carried by wind, produced by ocean spray and volcanic emissions, and plant matter and human activity. Even the cleanest seeming air contains thousands of these particles per cubic centimeter. Some particles are better condensation nuclei than others. Sea salt is particularly effective because it is hygroscopic. It naturally attracts water. Even at humidities below 100%, salt particles will accumulate water around themselves, creating tiny saline droplets. This is why clouds often form more readily over oceans or in maritime air masses. There is abundant sea salt to serve as nuclei. Sulfate particles from volcanic emissions and pollution are also effective nuclei. So are certain types of dust and organic particles from plants. Smoke from fires can seed cloud formation. Even bacteria and pollen can serve as nuclei, though they are less common and less efficient than salt or sulfate. When rising air reaches its dew point and becomes supersaturated, water molecules begin condensing onto whatever particles are present. Each particle becomes the center of a tiny droplet. Within seconds, billions of droplets form throughout the air mass as vapor condenses onto the available nuclei. The invisible vapor becomes visible cloud, all because of these microscopic specks that gave water something to condense onto. There is a strange irony here. Clouds, which we often think of as pure, as symbols of cleanliness, as heaven, sweet purity, require impurity to exist. Without dust and salt and pollution particles, without the air's contamination with solid matter, clouds could form. Rain itself needs imperfection to begin. The sky's dirt enables the sky's water. This has implications for weather and climate. Areas with more airborne particles can form clouds more readily, sometimes producing more rain. But if there are too many particles, you can create too many cloud droplets, each one smaller because the available water is divided among more nuclei. These smaller droplets are less likely to grow large enough to rain, so paradoxically, more nuclei can mean less rain. It is a delicate balance, pollution affecting precipitation in complex ways we're still learning to understand. But the basic principle is clear. Cloud formation requires something solid, something for vapor to condense onto. Pure water and pure air alone cannot make clouds. It takes impurity to make rain possible. Zoom in now down to the molecular scale. Watch what happens when a particle and water vapor meet at the moment of condensation. It is a slow dance at first, individual molecules finding their way to the particle's surface, one by one, beginning the process that will create a cloud droplet. Our particle, let's say it is a grain of sea salt about half a micrometer across, so small, you need a microscope to see it, is floating in air that has just reached its dew point. The air is saturated, unable to hold any more vapor without condensing. The relative humidity is 100%, meaning vapor pressure equals saturation vapor pressure. The stage is set. A water molecule moving randomly through the air happens to collide with the salt grain. The salt, being hygroscopic, holds on to the water molecule. The molecule doesn't bounce off, it sticks, attracted by the salt's electrical properties. It is joined almost immediately by another water molecule, then another. Within microseconds, the salt grain is coated with a thin film of water, just a few molecules thick, but enough to start the process. This thin water film dissolves some of the salt, creating a tiny saline droplet. More water molecules condense onto this droplet. The droplet grows, atom by atom, molecule by molecule. After a few seconds, the droplet might be a micrometer across, twice the size of the original salt grain, now mostly water with salt dissolved in it. Growth continues. The droplet is slightly hygroscopic because of the dissolved salt, which makes it attract more water. It is also now large enough to offer a substantial surface for vapor to condense onto. Water molecules continue arriving, colliding with the droplet's surface, sticking, being incorporated into the liquid. The droplet reaches 2 micrometers, then 5, then 10. At 10 micrometers, about 1/7 the width of a human hair, the droplet has reached typical cloud droplet size. It contains billions of water molecules, all organized into liquid structure, all held together by hydrogen bonds and surface tension. It is visible now, barely if you had a microscope. It reflects light. It has weight, albeit minuscule weight. It is a thing, a discrete object, not just scattered molecules. And this process is happening simultaneously on billions of particles throughout the rising air mass. Wherever there is a nucleation particle, a droplet forms. The air fills with these tiny droplets within minutes of reaching the dew point. Individually, they are nearly invisible, but collectively, they create the visible mass we call a cloud. What was clear air becomes white or gray cloud through the sudden appearance of countless droplets. Each one formed the same way, vapor condensing molecule by molecule onto a particle, building from microscopic to visible, creating liquid from gas. Our particular droplet, the one that will eventually fall as rain, has just been born. It is a cloud droplet now, small and suspended, drifting in the air, but it needs to grow much larger before it can fall. It has only begun its journey. The transformation from vapor to droplet is complete, but the transformation from droplet to raindrop has yet to begin. Pull back now. Zoom out from our single droplet forming on its salt grain and see the bigger picture. All around our droplet, the same thing is happening. Billions of other droplets forming on billions of other particles, all within the same rising air mass, all within minutes of each other. The air was clear. Now it is cloudy. The transformation happens that quickly when conditions are right. One moment you can see through the air, the next moment it is opaque with suspended droplets. If you were standing on a mountain and walked into this forming cloud, you'd experience it as sudden fog visibility dropping, everything becoming gray and damp, the world shrinking to just a few feet in any direction. From the ground looking up, you'd see a cloud appearing where there was clear sky moments before. Maybe it starts as just a wisp, a small patch of white, then it grows, spreading horizontally and vertically as more air rises into the condensation zone, more vapor condenses, more droplets form. Within 10 or 15 minutes, a small cumulus cloud might develop from nothing, a white puffy mass floating against blue sky. The cloud is just air with droplets. That is all it is. If you removed all the droplets, you'd be left with clear air, indistinguishable from the air surrounding the cloud. The droplets are the only difference between clear sky and cloud. They're what makes the cloud visible, what gives it form and substance. And these droplets are uniform in size, at least initially. They all started forming around the same time, from the same air, under the same conditions. Most are between 10 and 20 micrometers in diameter. None are large enough to fall. They're all held aloft by the air's turbulence and slight updrafts. The cloud is neutrally buoyant, neither sinking nor rising dramatically, just existing as a visible mass of suspended water. But the cloud is not static. Air currents move through it constantly. Updrafts bring new humid air into the cloud base, adding new vapor that condenses into new droplets. Downdrafts, or drier air at the edges, might cause some droplets to evaporate. Shrinking the cloud's shape shifts, bulging upward where updrafts are strong, flattening where they're weak, and the droplets themselves begin to interact. They drift through the cloud on air currents, and occasionally they collide with each other. When two droplets collide, they might merge, becoming one larger droplet. This process collision coalescence is the beginning of raindrop formation. It is slow at first, random, inefficient, but it is starting. Some droplets are already growing beyond the typical 10 micrometer size, becoming 20 micrometers, 30, larger. The cloud has come alive. It is no longer just a passive collection of droplets. It is a system, a process, something dynamic and evolving. Within this cloud, rain is beginning to form, not through any sudden event, but through the patient accumulation of droplets, colliding and merging, growing slowly toward the size needed to fall as rain. The invisible has become visible. Now the visible needs to become heavy enough to descend. The cloud continues to build. More humid air rises into its base, feeding it, keeping droplets suspended, or even lifting them higher. The cloud might grow taller, reaching upward from its initial altitude, stacking new levels on top of old as updrafts intensify. Or it might spread horizontally, existing as a thin layer or as disconnected puffs scattered across the sky. Inside the cloud, conditions vary. Near the base, where humid air is constantly entering, droplet formation is active, vapor still condensing onto nuclei. Higher up in the cloud, its interior droplets are mature, drifting with air currents, occasionally colliding. Near the top, in the coldest parts, some droplets might freeze, becoming ice crystals instead of liquid drops. The cloud's color, seen from outside, depends on thickness and droplet density. Thin clouds appear white, almost transparent, barely blocking sunlight. Thicker clouds appear gray, absorbing and scattering light, rather than transmitting it. The thickest clouds, the ones about to rain, appear dark gray or nearly black from below. Though from above, they still look white, reflecting sunlight back into space. But the cloud isn't T-raining yet. Despite being made entirely of water, despite looking heavy and full, it can T-rain until its droplets grow larger. 10 micrometer droplets can T-fall. They too light, too small, too easily held aloft by even gentle air currents. To become rain, these droplets need to grow to about 2,000 micrometers, 2 millimeters in diameter. They need to become 200 times larger than they currently are. That growth process is what happens next. Some droplets will undergo it successfully, becoming heavy enough to fall. Most 1T, they remain as cloud droplets until the cloud eventually dissipates, evaporating back into vapor without ever falling. But some will become rain. And the question is, how? How does a droplet grow from 10 micrometers to 2 millimeters? What process? What mechanism allows such dramatic growth? A cloud droplet, 10 micrometers in diameter, does technically fall. Everything with mass experiences gravity, but the droplet falls so slowly that it might as well be stationary. At this size, air resistance dominates gravity. The droplet drifts downward at about 1 centimeter per second, roughly half an inch per second. And this tiny fall rate is easily overwhelmed by the slightest updraft or turbulence. Think of it this way: falling from a cloud at 5,000 feet, at 1 centimeter per second, the droplet would take over 40 hours to reach the ground. 40 hours of falling, if it could maintain that rate. But it couldn't. Long before reaching ground, the droplet would encounter changing air conditions, different humidity levels. In drier air, it would evaporate completely within minutes. In rising air, it would be carried back upward, never descending at all. So cloud droplets don't fall. They drift, they hover. They get caught in turbulent eddies that carry them up and down and sideways within the cloud. They effectively weightless, their minimal mass unable to overcome the forces of air movement around them. This is why clouds persist. Their droplets can escape. They trapped by their own smallness. For a droplet to fall as rain, it needs to be much larger. Typical raindrops are 1 to 3 millimeters in diameter, 1,000 to 3,000 micrometers. That is 100 to 300 times the diameter of a cloud droplet. But here is the crucial part: volume and mass scale with the cube of diameter. A raindrop 3 millimeters in diameter isn't just 300 times wider than a cloud droplet. It is 27 million times more massive, 27 million times heavier. This massive raindrop falls much faster, about 20 miles per h, for a typical 3 millimeter drop. At this speed, air resistance still limits the fall rate, which is why raindrops reach terminal velocity and keep accelerating. But updrafts can no longer hold them aloft. Gravity wins. The drop descends through the cloud and out its base into clear air below, falling toward ground at a rate that will bring it down in minutes rather than hours. So the fundamental problem for rain formation is growth. Cloud droplets need to grow enormously, not just become a bit larger, but achieve a massive size increase. They need to collect enough additional water to increase their mass by millions of times. And they need to do this while floating inside a cloud with no obvious source of additional water except other droplets or vapor around them. Nature has found two main ways to achieve this growth. One is collision, coalescence, droplets bumping into each other and merging, growing through accumulation. The other involves ice crystals growing at the expense of liquid droplets in cold clouds. Both processes are slow, probabilistic, dependent on specific conditions. But when they work, they transform tiny suspended droplets into drops heavy enough to escape the cloud's grasp and fall as rain. The growing process is where rain actually forms, where the transition from cloud to precipitation occurs. Inside a cloud, droplets are in motion. They don't sit still. Air currents carry them constantly, rising, falling, swirling, moving in 3 dimensions through the cloud's interior. And as they move, occasionally they encounter each other. 2 droplets' paths intersect. They collide. Sometimes, the collision results in nothing. The droplets bounce off each other, surface tension keeping them separate, and they drift apart again. The air flowing around them creates cushioning, pushing them apart before they can touch. This is common with similarly sized droplets moving at similar speeds. There is not enough momentum to overcome the air cushion between them. But sometimes, the droplets do merge. One absorbs the other, and now there is a single larger droplet where there were two smaller ones. This is coalescence. It is not inevitable. The conditions have to be right, but it happens often enough to matter, and when it does, it is the beginning of raindrop formation. The newly merged droplet is slightly larger than its components. If two 10-micrometer droplets merge, the result is about 13 micrometers, larger but not dramatically so. The merged droplet's mass is double that of either original droplet, but its diameter increased only 30%. Volume scales with radius cubed, so doubling volume doesn't double radius. But here is where the process becomes interesting. A larger droplet falls slightly faster through the cloud than a smaller droplet. Not much faster. A 13-micrometer droplet might fall at 1.2 centimeters per second instead of 1.0, but faster. And because it is falling faster, it sweeps through more air, encountering more droplets in its path. Its collision rate increases. The larger droplet collides with a third droplet. They merge. Now it is even larger, falling even faster, encountering even more droplets. It collides with a fourth, then a fifth. Each merger makes the next merger more likely. Growth accelerates. This is a positive feedback loop. The bigger the droplet gets, the faster it grows. But the loop is slow. Even with accelerating growth, it takes time. A droplet might spend 20 or 30 minutes inside a cloud, colliding dozens or hundreds of times before it reaches raindrop size. And that is if it is lucky. Most droplets don't undergo this runaway growth. They drift without colliding much, remaining small, eventually evaporating when the cloud dissipates or drifts into drier air. The droplets that do grow are the lucky ones, the ones that happen to be slightly larger to start with, or happen to be in regions of the cloud, with stronger updrafts and downdrafts that enhanced collision rates. Random chance plays a huge role. There is no intention, no guided process, just probability and physics. Watching this process in slow motion, if you could, would be mesmerizing. Billions of droplets drifting through gray mist, occasionally touching and merging, a few of them growing steadily, while most remain small. It is like watching a lottery being drawn, droplet by droplet, merger by merger, with only a tiny fraction of droplets winning the rain lottery and growing large enough to fall. And our particular droplet, the one that will become the raindrop on your window, is one of the lucky ones. It is growing, colliding, collecting other droplets, becoming heavier with each merger, falling faster, accelerating toward the size threshold, where it can escape the cloud. Our droplet's luck began early. When it first formed, condensing onto a sea salt grain, that grain happened to be slightly larger than average. This meant the initial droplet was also slightly larger, maybe 12 micrometers instead of 10. A small advantage, barely significant, but enough to matter. Because it was slightly larger, it fell slightly faster. At 12 micrometers, maybe 1.3 centimeters per second instead of 1.0. And because it fell faster, its path through the cloud intersected with more other droplets. Paths within the first minute, it had already collided and merged with 3 other droplets. Now it was 15 micrometers, falling at 1.8 centimeters per second. The growth continued. By 5 minutes, it had reached 20. 5 micrometers through a series of successful collisions. By 10 minutes, 40 micrometers. The acceleration was becoming noticeable. Its fall speed had doubled, tripling its collision rate. Now it was collecting droplets not just through random chance, but almost continuously, sweeping through the cloud like a tiny vacuum. At 15 minutes, the droplet reached 100 micrometers, 0.1 millimeter, 10 times its starting size, 1,000 times its starting mass. This is called a drizzle drop, large enough to fall faster than typical updrafts, beginning to descend through the cloud rather than being held within it. But it is still not rain-sized. It needs to keep growing. The droplet's path carries it through the thickest part of the cloud, where droplet density is highest. It is collecting dozens of droplets per second now, each collision adding fractionally to its mass. At 20 minutes, it is 300 micrometers. At 25 minutes, 600 micrometers. more than half a millimeter, approaching rain size. Throughout this growth, the droplet has been falling through the cloud, descending toward its base. The cloud is maybe 2,000 feet thick vertically, and the droplet has traversed most of that distance while growing. Near the cloud base, air is slightly warmer. Droplets are slightly larger, on average. Collision efficiency is higher. The final stage of growth happens quickly. At 30 minutes after formation, the droplet reaches 1 millimeter, officially a raindrop, large enough to survive falling through clear air without evaporating immediately. But it continues growing. At 35 minutes, it is 1.5 millimeters. At 40 minutes, 2.2 millimeters. A large raindrop, falling at about 18 miles per H-hour, too heavy for any atmospheric updraft to support. The droplet, now definitely a raindrop, emerges from the cloud base below is clear air, warmer and drier. A drop begins falling through empty sky, no longer colliding with cloud droplets because it has left the cloud behind. It is now in free fall, accelerating briefly before reaching terminal velocity, descending the remaining thousands of feet to ground level, 40 minutes from condensing onto a salt grain to exiting the cloud as rain. Most of that time spent inside the cloud, drifting and colliding and growing. The journey from 10 micrometers to 2 millimeters, from weightless droplet to falling raindrop, from vapor made visible to precipitation. Our droplet got lucky. Most don't. Most remain small, never achieving the runaway growth necessary to rain. But this one did, and because it did, it will reach your window, adding its small percussion to the sound of rain that helps you sleep. There is another way for rain to form, particularly common in clouds that extend into freezing temperatures. Instead of liquid droplets slowly colliding and merging, ice crystals form and grow rapidly through a completely different process. Many of the heavy rains you've experienced began not as liquid water at all, but as snowflakes that melted on their way down. In clouds colder than about 14 degrees Fahrenheit, ice crystals form directly from vapor without going through a liquid phase. This is deposition, the reverse of sublimation, where water molecules transition directly from gas to solid. Special particles called ice nuclei, usually dust or mineral particles with structures similar to ice crystals, serve as templates for ice formation. But the interesting situation happens in clouds between about 14 degrees Fahrenheit and 32 degrees Fahrenheit, where both liquid droplets and ice crystals coexist. These are called mixed phase clouds, and they re-rain factories. Here is why. Ice crystals and liquid droplets can both exist at the same temperature, but they re-not in equilibrium. Water vapor slightly prefers to condense onto ice rather than liquid water at these temperatures. It is a quirk of thermodynamics related to the energy states of different phases. This creates a bizarre situation. Ice crystals and liquid droplets are floating in the same air, surrounded by the same water vapor, but the vapor pressure necessary to maintain the droplets is slightly higher than the vapor pressure necessary to maintain the ice crystals. So the air can be saturated with respect to liquid water, but supersaturated with respect to ice. What happens? The ice crystals grow. They pull water vapor directly from the air, depositing it onto their surfaces as solid ice. Meanwhile, the liquid droplets shrink, they re-evaporating, releasing water vapor, which is then captured by the growing ice crystals. The droplets are losing mass to feed the crystal's growth. This process is remarkably efficient. An ice crystal can grow to snowflake size, several millimeters across, in just 10 or 15 minutes. That is much faster than collision, coalescence, which might take 40 minutes to grow a raindrop. The ice crystals become heavy enough to fall, descending through the cloud, often collecting supercooled liquid droplets that freeze onto them instantly, adding more mass. If the ice crystal falls through air warmer than 32 degrees Fahrenheit, it melts, becoming a large liquid raindrop. This melting usually happens fairly high up, thousands of feet above ground in most climates, so by the time the drop reaches you, you'd never know it was once ice. It is just rain, indistinguishable from rain formed entirely as liquid. This ice crystal process is called the Bergeron process or the Wegener. Bergeron, Findeisen process, after the scientists who figured it out. It is responsible for much of the rain in mid-latitudes. Most of the rain you've experienced in temperate climates began as ice or snow high in the cloud, even on warm summer days. So rain can form two ways: warm rain process through collision, coalescence in clouds where all water is liquid, or cold rain process through ice crystal growth and melting in mixed phase or ice clouds. Both create the same end result, drops heavy enough to fall, but through very different paths. Nature is flexible, using whichever method the temperature profile allows. There is a threshold, a critical size where a droplet transitions from being held by the cloud to being released by it. That threshold is roughly 2 millimeters in diameter, though it varies depending on updraft strength and other factors. Below this size, the droplet can be kept aloft by atmospheric turbulence. Above it, gravity wins decisively. A 2-millimeter raindrop is visible to the naked eye if you are looking carefully, about the size of a pinhead, small but definitely perceptible. It weighs about 4 milligrams, which seems negligible, but it is enough. At this size, the drop falls at about 16 to 18 miles per HR at sea level, fast enough that typical updrafts can T-hold it. The shape of the drop at this size is no longer spherical. Small droplets are sphere-shaped surface tension, pulling them into the minimum surface area configuration. But raindrops larger than about 1 millimeter begin to deform. Air resistance pushing up on the bottom flattens them into a shape more like a hamburger bun, rounded on top, flattened on bottom. The larger they get, the more pronounced this flattening becomes. Very large raindrops, over 5 millimeters, become unstable. The flattening becomes extreme. The drop takes on a parachute shape with a concave bottom, and eventually it breaks apart into smaller drops. This is why you don't see raindrops larger than about 6 millimeters. They can maintain cohesion at that size while falling. The aerodynamic forces tear them apart. Most raindrops you experience are between 1 and 3 millimeters. Drizzle drops are smaller, 0.2 to 0.5 millimeters, barely large enough to fall, but not heavy enough to make much noise when they land. The drops from heavy downpours can be 4 or even 5 millimeters, large enough to sting slightly when they hit skin, large enough to splash dramatically when they strike pavement. The transition from cloud droplet to raindrop is complete when the drop reaches this critical size and begins falling out of the cloud. It has crossed a threshold from suspended to falling, from cloud constituent to precipitation. It is no longer part of the cloud. It is separate, individual, descending. For our particular droplet, this moment arrives about 40 minutes after it first condensed in the cloud. It is grown from 10 micrometers to 2.5 millimeters, increased its mass by over 15 million times, and transitioned from drifting to falling. The collision-coalescence process has done its work. The droplet is now a raindrop, heavy and descending, shaped like a small hamburger bun by air pressure, falling at 18 miles per HR toward the Earth's surface, below the cloud. Clear air awaits. The drop will pass through this clear air, through different temperature zones, possibly through wind shear that will push it sideways, definitely through air of varying density and humidity. The fall from cloud base to ground will take about 5 to 10 minutes, depending on the cloud's altitude. That is the descent phase, the final journey, the last leg of the trip from vapor to condensation to rain. And it begins now, with the drop exiting the cloud's gray confines and entering the clear air below. The moment of exit is subtle but definitive. The raindrop passes through the cloud's lower boundary, emerging from gray mist into clearer air below. Around it, the density of water droplets suddenly decreases. It is no longer surrounded by billions of other droplets. Now it is mostly alone, falling through empty air with occasional other raindrops nearby, all descending together but separately. The light changes. Inside the cloud, everything was diffuse and gray. Sunlight scattered by countless droplets into a uniform glow without direction. Below the cloud, light has source and shadow again. If it is daytime, the raindrop falls through illuminated air. If it is night, it falls through darkness, punctuated perhaps by city lights below or lightning flashes from the cloud above. The drop accelerates initially, gaining speed as it exits the cloud's turbulent interior and enters smoother air. But acceleration doesn't continue long. Within seconds, the drop reaches terminal velocity. the speed where air resistance exactly balances gravity, where further acceleration stops. For a 2.5 mm drop, terminal velocity is about 18 miles per h-hour, or about 8 meters per s-econ. At this speed, air flows around the drop in complex patterns. The front of the drop pushes air aside, creating a region of high pressure. Air flows around the sides and meets again behind the drop in a turbulent wake. This airflow creates the flattening effect, pushing up on the drop's bottom more than on its top, deforming the sphere into that hamburger. The drop is stable, though. Its surface tension is strong enough to hold it together despite the aerodynamic forces. It wobbles slightly as it falls, oscillating gently, but it doesn't break apart. It is a cohesive unit, 2.5 millimeters of liquid water falling as one, all its molecules held together by hydrogen bonds and surface tension. Temperature begins to affect the drop now. Inside the cloud, the drop was at the cloud's temperature, perhaps 40 degrees Fahrenheit. As it falls into warmer air below, it absorbs heat from its surroundings. The warming is gradual. Water has high heat capacity, so it takes time to change temperature, but real. By the time the drop reaches ground, it might be 10 or 15 degrees warmer than when it left the cloud. The drop passes through the altitude, where airplanes fly when landing or taking off. It is invisible to pilots, just one among millions of drops falling in this rain shower, each one following its own ballistic trajectory toward Earth. From inside an airplane, passengers would see only the effect: rain streaking across windows, drops merging and flowing. In streams, the ground below visible only as a gray blur through the precipitation. The fall has truly begun. No more floating, no more being held in suspension, just gravity and air resistance, descent and destination. The drop is committed now to its trajectory, to its landing, to the completion of its journey from ocean to cloud to Earth. Several thousand feet below, the ground awaits. Soil or pavement or water or leaf, some surface, where the drop will strike and complete this particular cycle of its existence. The atmosphere is not uniform. As the raindrop falls, it passes through layers of air with different temperatures, densities, and compositions. Each layer affects the drop in subtle ways, even if the drop maintains its general downward trajectory throughout. In the first 1,000 feet below the cloud, the air might be relatively cool and humid. This is why the cloud base formed at this altitude in the first place. The drop falls through air not too different from the cloud's interior, just less saturated, containing vapor, but not enough to form new droplets. The humidity here might be 80% or 90%, high enough that the drop loses almost no mass to evaporation. Descending further, the drop enters warmer air. Temperature might increase by 10 or 15 degrees over the next few thousand feet. Warmer air can hold more moisture, which means it is usually less humid in relative terms, even if it contains the same amount of vapor. At 60% or 70% humidity, the drop begins to lose water molecules from its surface. They evaporate into the surrounding air, slightly shrinking the drop's size. The evaporation is slow. The drop might lose a few percent of its mass during the entire descent, but it is constant. Molecules at the surface, moving fast enough, break free. This evaporative cooling slightly lowers the drop's temperature, even as the surrounding air is warm. The drop becomes a tiny cooling unit, absorbing heat from air and using it to evaporate surface water, a miniature version of how sweat cools your skin. If the air below the cloud is particularly dry, the evaporation can be dramatic. This is what creates virga, rain that never reaches the ground because it evaporates completely during its fall. From the ground, virga looks like dark streaks beneath clouds, rain that seems to stop in mid-air, dissolving into nothing, but in more humid conditions. Drops survive the journey, losing some mass but remaining cohesive. The drop also encounters varying air densities. Near the surface, air is denser, more molecules per unit volume, more mass per unit volume, which increases air resistance. The drop's terminal velocity actually decreases slightly as it descends into denser air. At high altitudes, raindrops fall faster. Near the surface, they fall slightly slower. The difference isn't too dramatic, but it is real. Another subtle variation in the fall's physics: wind affects the drop too. Horizontal wind pushes the drop sideways as it falls. Strong winds can carry raindrops far from where they de-land in still air. A drop exiting a cloud at 10,000 feet in a 30-mile-per-hour wind might land a mile downwind from its exit point. The fall is mostly vertical, but there is horizontal motion too, the drop tracing a diagonal or even a curve through the sky depending on how wind varies with altitude. And there are thermals, updrafts and downdrafts, columns of rising and sinking air. A drop passing through an updraft momentarily slows, fighting against air moving upward. Through a downdraft, it accelerates, pulled down faster by air already sinking. The drop's path is affected by these invisible currents, its fall time varying by seconds, depending on what air motions it encounters. Terminal velocity isn't a single number. It varies by drop size, air density, and altitude. But for a typical raindrop of about 2.5 millimeters, falling through sea-level air, terminal velocity is approximately 18 miles. 18 miles per h-hour is a jogging pace, easy to match on a bicycle. It seems like rain should fall faster, should plummet dramatically. But physics limits the speed. The limitation comes from air resistance. As the drop falls, it pushes air out of its way. This creates drag, a force opposing the motion, proportional to velocity squared. The faster the drop moves, the more drag it experiences, and the relationship is exponential. Double the speed and drag quadruples. Initially, when the drop first exits the cloud, drag is small and gravity dominates. The drop accelerates, gaining speed. But as speed increases, drag increases faster. Eventually, drag force equals gravitational force. At this point, net force on the drop is zero. With no net force, acceleration stops. The drop continues at constant velocity, terminal velocity. For our 2.5 millimeter drop, terminal velocity is reached within about 6 seconds of leaving the cloud. 6 seconds and maybe 300 feet of falling, and then speed stabilizes. The rest of the descent happens at this constant pace, 18 miles per h-hour, covering about 8 meters per second, taking roughly 5 to 7 minutes to fall from typical cloud base altitudes of 2,000 to 3,000 meters. Smaller drops have lower terminal velocities. A drizzle drop of 0.5 millimeters might fall at only 4 or 5 miles per h-hour, a slow walking pace. It takes much longer to reach ground, and it is much more vulnerable to evaporation or being carried back upward by updrafts. This is why drizzle feels different from rain. The drops arrive more slowly, more gently, with less impact force. Larger drops fall faster. A 4 millimeter drop might reach 22 miles per h-hour. But as mentioned earlier, drops much larger than 5 millimeters become unstable and break apart. So there is an upper limit to both raindrop size and fall speed. The fastest raindrops fall at about 25 miles per h-hour, and even that is rare. The drop S-shape affects its terminal velocity too. The flattening caused by air resistance actually increases drag, which lowers terminal velocity compared to if the drop remained spherical. A perfectly spherical 2.5 millimeter water drop would fall slightly faster than a real raindrop, which is flattened and experiences more air resistance because of its larger cross-sectional area. Terminal velocity also explains why rain doesn't hurt despite falling from great heights. Drops reach their maximum speed quickly, then maintain it. They are not continuously accelerating all the way down. If they fell in a vacuum without air resistance, drops from 10,000 feet would strike ground at over 500 miles per h-hour with devastating force. Air resistance saves us from this, limiting drops to gentle speeds, keeping rain pleasant rather than painful, making the sound of precipitation a soft percussion rather than violent impact. How long does rain take to fall? It is a question most people never consider. Rain just appears falling from the sky, and we don't think about the time involved in its descent. But every raindrop spends several minutes in free fall between cloud and ground, and those minutes are part of its journey. Consider our 2.5 millimeter drop exiting a cloud at 8,000 feet altitude, a typical height for rain clouds in temperate regions, falling at 18 miles per h-hour, or about 8 meters per second. The drop descends through 2,400 meters of air. Simple math, 2,400 meters divided by 8 meters per second equals 300 seconds. That is 5 minutes of falling. 5 minutes is longer than you might expect. It is enough time to make a cup of tea, to walk 2 or 3 city blocks, to listen to a full song. The raindrop spends this entire time suspended in motion, descending but not yet arrived, between cloud and earth, committed to its trajectory, but not yet at destination. During those 5 minutes, the drop travels not just vertically, but horizontally, carried by wind. In a 20-mile-per-hour breeze, the drop drifts nearly 2 miles sideways during its fall. It exits the cloud at one location and lands at another, sometimes far enough away that the cloud isn't even overhead when the rain arrives. This is why you can sometimes feel rain while seeing clear sky above. The rain is falling from a cloud that is blown elsewhere, the drops drifting downwind as they descend. The duration varies with altitude and drop size. Higher clouds mean longer falls. Drops from clouds at 20,000 feet might fall for 15 or 20 minutes, though most would evaporate before reaching ground, unless the air is quite humid. Lower clouds mean shorter falls. Rain from stratus clouds at 2,000 feet might reach ground in just 2 minutes. Smaller drops take longer to fall because they have lower terminal velocities. A drizzle drop at 5 miles per HR might take 15 or 20 minutes to descend from 8,000 feet, and often it does evaporate before completing the journey. This is why drizzle requires low clouds. Small drops can survive, falling from high altitudes. During the fall, the drop is in a state of isolated existence. It is no longer part of a cloud, not yet part of a puddle or stream. It is individual, separate, just one drop among millions falling in the same rain shower, but each on its own path, if the drop had consciousness, which of course it does. This might be its moment of independence, no longer collective cloud droplet, not yet merged into surface water, just drop. The duration of the fall is also the duration of the sound of rain. Each drop that strikes your window or roof has been falling for several minutes. The sound you hear is the conclusion of a 5-minute journey, the percussion of arrival after an airborne voyage that covered vertical miles and horizontal distance, descending through layers of atmosphere, approaching ground inexorably, finally striking surface and creating the sound that helps you sleep. In its 5-minute descent, the raindrop passes through a vertical slice of the world, a column of atmosphere that contains more than just air. There is life at multiple altitudes, phenomena at different heights, an invisible architecture of atmospheric layers that the drop traverses on its way down. At the highest point, just below the cloud base, there might be birds. Swallows and swifts feed on insects at these altitudes, flying through the rain, unbothered by the falling water. The drop passes near them, maybe even strikes one, becoming a momentary spot of wetness on feathers before shaking loose and continuing its fall. Birds in rain are curious. They continue flying, hunting, seemingly unaffected by the drops, navigating by vision through precipitation that must reduce visibility. Lower, at around 6,000 to 8,000 feet, small insects sometimes drift. These aren't too strong flyers. They rear more like aerial plankton, carried by air currents, ascending in updrafts and descending in downdrafts. During rain, most insects seek shelter, but some are caught aloft. The drop passes through this sparse insect layer, occasionally colliding with a gnat or midge, the impact negligible to the drop's trajectory, but probably catastrophic for the insect. At mid-altitudes, around 3,000 to 5,000 feet, aircraft sometimes fly. Small planes, helicopters, birds again. Larger ones, this time crows and hawks and gulls. The drop is one of millions in a curtain of rain that these flyers navigate through. From a pilot's perspective, the drops are a blur on the windscreen, a streaming effect that makes landing more difficult, but not impossible. From the drop's perspective, if it had one, the aircraft is a fast, moving obstacle that passes in an instant, creating turbulence, but not interrupting the fall. Lower still, entering the boundary layer of the atmosphere, where human activity dominates, the drop passes by buildings, through tree canopies, past power lines and towers. If it is falling in a city, the drop descends through urban airspace, past high-rise windows where people might be looking out at the rain, past rooftop gardens and cell towers, through the layer where birds roost on ledges and where wind patterns become chaotic, due to buildings disrupting smooth airflow. In the final 1,000 feet, the drop enters human breath level, the altitude where we live and move. It passes through air we might be breathing if we were outside, air that smells like wet earth or pavement. air that carries the sounds of surface activity. Traffic, voices, the sound of rain striking surfaces already wet. And throughout the descent, there is the temperature gradient, the humidity gradient, the changing quality of light. Higher up, light is brighter, less filtered. Lower down, especially near ground in rain, light is dim, gray, diffused. The drop passes from relative brightness to relative darkness, from thin air to thick, from cold to warm, from the meteorological realm to the surface realm. It is a journey through layers, through zones, through the vertical structure of the lower atmosphere. And at the end, ground approaches, solid earth, the final destination. The place where the drop's airborne journey concludes and its surface journey begins. In the final minute of its fall, the drop descends through the last 1,000 feet of air. The ground is visible now, not to the drop, which has no vision, but to an observer watching the drop. Surface features become distinct. The texture of a roof, the pattern of pavement, the leaves of trees, the ripples of puddles already forming. The drop is committed to its landing point now. Its horizontal drift has mostly determined where it will strike. If there is wind, the drop has been carried sideways during its entire descent, and its landing location might be hundreds of feet downwind from where it exited the cloud. But in this final 1,000 feet, there is not enough distance left for wind to push it significantly further. The target is essentially fixed. The air thickens as the drop descends. At surface level, atmospheric pressure is highest. All the weight of the air above is pressing down, compressing the lowest layer into greater density. The drop's terminal velocity decreases slightly, maybe from 18 to 17 miles per h-hour as the thicker air provides more resistance. The change is subtle but measurable. Temperature continues to warm the drop. If it is a summer rain, the drop might have started its fall at 40 degrees and be approaching 60 degrees by the time it nears ground. The warming is sensory. When rain strikes your skin, you can sometimes feel whether it is warm rain or cold rain, depending on how much temperature change occurred during the descent and what the drop's starting temperature was. The drop crosses through the final layer, the last 100 feet, then 50, then 20. The ground rushes up, or from the drop's reference frame, the drop rushes down towards stationary Earth. The impact is imminent, inevitable, seconds away. The drop has fallen for 5 minutes, traveled thousands of vertical feet, drifted laterally, perhaps a mile or more, descended through temperature zones and humidity gradients and wind shears. It has survived the fall without evaporating, without breaking apart, maintaining cohesion and mass and momentum. And then, in the final second, the final 10 feet, the final instant, surface is right there. The drop can see it coming, can sense through air pressure changes that impact is imminent. The ground might be pavement or grass or a puddle or a leaf or your window. The drop doesn't know and can't choose. It is simply falling, and whatever is below will be what it strikes. The moment before impact, the drop is still intact, still 2.5 millimeters of liquid water, still moving at 17 miles per h-hour, still shaped like a small hamburger bun by air resistance. It has completed its atmospheric journey. The condensation in the cloud, the growth through collision or ice processes, the exit from the cloud, the long fall through air. All of these are finished. What remains is the impact, the landing, the transition from falling drop to surface water, and then it strikes. The airborne phase ends. The surface phase begins. And the journey, at least this particular segment of it, concludes with a small splash or absorption. The drop joining whatever water already exists at the surface, beginning the next chapter of its cycle. Every raindrop lands somewhere specific, not just on the ground in general, but on a particular surface with particular properties, and where it lands determines what happens next, whether the water soaks in or runs off, whether it stays separate or merges with other water, whether it evaporates quickly or persists for hours. Some drops land on leaves. Trees intercept rain before it reaches ground, their canopies catching drops mid-fall. A drop striking a leaf might roll off immediately, sliding along the leaf's waxy surface, collecting in a larger drop at the tip, eventually dripping to a lower branch or to the ground below. Or it might stay on the leaf surface, held by surface tension in a small dome, sitting there until evaporation takes it back into air without it ever reaching soil. Other drops strike roofs, metal roofs, shingle roofs, tile roofs, flat membrane roofs. Each surface sounds different, feels different to the drop. Metal roofs are hard and resonant, creating that distinctive drumming sound, drops bouncing and splashing before flowing toward gutters. Shingled roofs absorb some impact, softening the sound, holding drops briefly before they slide downward. The drop's energy is distributed differently depending on the surface's hardness and absorbency. Pavement receives enormous amounts of rain in developed areas. Drops strike concrete sidewalks, asphalt roads, brick patios. These surfaces are impermeable. Water can't soak in, so drops either evaporate, puddle, or flow along surface gradients toward drains and curbs. In cities during heavy rain, you can see sheets of water flowing along streets, thousands of drops merged into continuous flow, all moving downhill together, overwhelmed drainage systems creating urban rivers that weren't there minutes before. Soil is where many drops ideally land from the perspective of ecosystems and agriculture. Drops strike bare earth, splash slightly, then begin infiltrating, soaking into the spaces between soil particles, moving downward through capillary action and gravity. The infiltration rate depends on soil type. Sandy soil absorbs quickly, clay soil slowly, compacted or frozen soil barely at all. Rain on good soil is quiet, almost silent. The drops absorbed, without much splash or sound. Water landing on water is common too. Ocean surfaces, lakes, rivers, puddles, wherever standing water exists, rain adds to it directly. The drop merges instantly with the surface, creating a brief ring of ripples that expands outward before dissipating. In heavy rain, water surfaces become textured with overlapping rings, a constantly changing pattern of circular waves emanating from countless impact points. The surface never still, always responding to new drops arriving. And some drops land on human skin, on clothing, on cars, on windows. These are the drops we notice most directly, the ones we feel and see. A drop on skin creates a small tactile sensation, a momentary coolness. A drop on a window slides down, leaving a wet trail, merging with other drops, creating those streaming patterns that you can watch from inside while staying dry. 1,000 different surfaces, 1,000 different receptions. Each drop's landing unique in its specifics, even if the physics is universal. Rain makes sound. Not just one sound, but many, each determined by what surface the drops are striking and how large the drops are. The sound of rain is actually a complex layering of thousands of individual impacts happening near, simultaneously, creating the perception of a continuous sound even though it is actually discrete events overlapping. Rain on a metal roof is loud. Each drop hits the metal with a distinct impact, creating a brief percussion. The metal resonates slightly, amplifying the sound. Large drops create deeper tones, smaller drops higher pitches. In heavy rain, the individual impacts blur into a roar, like sustained drumming, the rhythm too fast for the ear to separate into distinct beats. It is an encompassing sound, filling the space beneath the roof, impossible to ignore. This is the sound that wakes you in the night or makes conversation difficult in a tin-roofed structure. Rain on leaves is softer but complex. Each leaf struck produces a subtle tap, dampened by the leaf's flexibility. A tree full of leaves creates a rustling whisper, thousands of small impacts, creating a sound like sustained static or distant applause. The pitch varies depending on the leaf size and stiffness. Large soft leaves create deeper tones, small stiff leaves higher ones. Walking through forest during rain, you're surrounded by this layered rustling from all directions and heights. Rain striking canopy far above and understory at eye level, creating an immersive acoustic environment. Rain on pavement makes a splashing sound. The drops hit hard surface and break apart slightly, creating small splashes of liquid and air mixed together. The sound has a wet quality, distinctly different from the dry percussion of rain on metal. On large paved surfaces like parking lots or plazas, heavy rain creates what sounds like frying, a crackling, splattering sound from hundreds of simultaneous impacts and splashes. The sound is both rhythmic and chaotic, patterns within randomness. Rain on water is quieter. Drops striking a lake or puddle create small plunking sounds, higher pitched than rain on solid surfaces. because the water surface yields and the impact creates a cavity that collapses. The sound is almost musical, like an abstract percussion instrument. In light rain, you can hear individual plunks. In heavy rain, they merge into a continuous pattering that seems to emanate from the water surface itself, the lake or puddle speaking in response to rain's impact. Rain on soil is nearly silent. The earth absorbs both the drop and the sound of its impact, creating just a whisper, a gentle patter if you're close enough to hear. This is the quietest rain, rain that falls on fields and forests and gardens, doing its work without announcing itself, watering the ground with minimal sound. You have to listen carefully to hear it, to detect the subtle impact of drops on earth. And rain on your window is intimate. Drops striking glass create soft taps, sometimes sliding sounds as drops stream down the pane. It is the sound you hear from inside, lying in bed, the sound that creates that sense of shelter and separation. The weather is happening out there, you're safe in here, and the window between is where the two worlds meet audibly. When rain falls on the ocean or a lake or a river, or even a puddle, something interesting happens. Water returns to water. The drop that has been individual since it left the cloud suddenly merges back into a collective body. Its identity as a separate drop ends. The molecules it contains disperse into the larger water mass, mixing with billions of other molecules, becoming indistinguishable from the water that was already there. The impact creates a brief disturbance. The drop strikes the surface and creates a small cavity, a dimple in the water surface, where the drop's momentum pushes surface water downward and aside. This cavity exists for just milliseconds before surface tension and gravity collapse it. As it collapses, it sometimes creates a tiny jet or splash upward, a small crown of water that briefly rises above the surface before falling back. The cavity's collapse also creates ripples, concentric circles of waves that propagate outward from the impact point. These ripples are small, maybe a millimeter in amplitude, but they travel across the surface at surprising speed, expanding outward in perfect circles until they dissipate or interfere with other ripples from other drops. In steady rain, the surface of water becomes a complex interference pattern, overlapping circles creating temporary geometric designs. The surface never flat, always textured by rain's constant arrival. The sound of rain on water is distinctive. Each impact creates a small plunking tone, caused by air being trapped briefly beneath the drop before escaping as a tiny bubble. The frequency of the sound depends on the size of the cavity, and bubble lager drops create deeper plunks, smaller drops higher-pitched ones. A rain shower over a lake creates what sounds like a massive percussion instrument, thousands of notes playing simultaneously, and ambient music created by water striking water. Below the surface, rain's impact can be detected several inches down. Fish can sense the vibrations, the pressure waves from drops striking above. Heavy rain might drive surface-feeding fish deeper, away from the turbulence. The impact mixes the very top layer of water, incorporating the falling drops into the top few centimeters, slightly cooling the surface, because raindrops are usually colder than the water body they're falling into. For the ocean, rain is returning home. The water that evaporated from the ocean days or weeks ago, that rose as vapor, formed clouds, fell as rain. That water is now back where it started. It has completed one loop of the cycle. The salt it left behind during evaporation is still here, waiting. The drop mingles with salty water, absorbs salt again, becomes part of the ocean once more. Maybe it will remain here for weeks or months before evaporating again. Maybe it will be carried by currents to another part of the ocean. Maybe it will sink to depth, becoming part of the deep ocean's slow circulation that might keep it submerged for centuries. Rain on water is return. Reunion, the completion of a journey that returns the traveler to origin. The drop came from water, it returns to water, and the cycle continues, endless and ancient. When rain falls on soil, the most productive thing from most ecosystems' perspectives happens. The water infiltrates. It soaks in, moving from surface into the ground, entering the soil's porous structure, beginning a journey into the earth that might eventually lead to underground aquifers, or might be absorbed by plant roots long before going that deep. The infiltration begins immediately. The drop strikes soil and spreads into a small wet spot. Water molecules begin moving between soil particles, around grains of sand, through tiny spaces between clay platelets, into the organic matter, mixed through the soil. The movement is driven by gravity, pulling downward, and capillary action, pulling in all directions. Water attracted to soil particles surfaces, spreading through the available pore space. Sandy soil has large pores between particles. Water moves through it quickly, draining well, soaking in so fast that puddles rarely form. A sandy beach absorbs rain almost as quickly as it falls. Clay soil is the opposite. Tiny particles packed tightly, tiny pores. Rain on clay tends to puddle, to run off, to sit on the surface because it can't infiltrate fast enough. The ideal soil for agriculture is loam, a mixture of sand, silt, and clay that balances drainage with water retention. Loam absorbs rain readily but holds some of it in pore spaces rather than draining completely, making water available to plant roots over time. Good garden soil soaks up rain like a sponge, darkening with moisture without becoming waterlogged. As water infiltrates, it carries things with it. Dissolved minerals from the rain itself, trace elements that condensed with the water, surface nutrients, nitrogen, phosphorus, organic compounds from decomposing plant matter. The infiltrating water becomes soil solution, a dilute mixture of water and dissolved substances that feeds the soil ecosystem. This descending water encounters roots. Plant roots absorb water through tiny root hairs, taking up water molecules and dissolved nutrients, pulling them into the plant's vascular system. The water begins moving upward again, from soil into root, into stem, into leaf, where it might eventually evaporate through stomata, in a process called transpiration, returning to atmosphere to begin the cycle again. Water that doesn't get absorbed by roots continues deeper. It moves through subsoil, through layers of increasing density and decreasing organic content, following pore spaces and fractures downward. Eventually, if it goes deep enough, it reaches the water table, the level where all pore spaces are completely saturated with water, the top of the groundwater zone. This is aquifer recharge, rain becoming groundwater, entering the slow, deep circulation of water that moves underground through rock and sediment layers. The journey from surface to water table might take hours in sandy soil or weeks in clay, and the depth might be just a few feet or hundreds of feet, depending on local geology. But the principle is the same. Rain falling on earth soaks in, moves downward and sideways, becomes part of the soil moisture and groundwater systems that feed springs and streams and wells. Rain on soil is rain becoming available to terrestrial life, entering the systems that support forests and crops and all the life that depends on soil-stored water. Urban rain has a different character than rural rain. Cities replace absorptive natural surfaces with impermeable human materials. Concrete, asphalt, metal, glass. The majority of urban surfaces don't absorb water, they shed it. So rain in cities flows more than it soaks, creating runoff patterns that can be dramatic and sometimes problematic. A raindrop falling in a city likely lands on pavement or a building. If it hits a roof, it flows to a gutter, then through a downspout, then either onto the ground or directly into a storm drain. If it hits a street, it flows along the pavement slope toward the curb, into the gutter, toward a drain inlet. The drop is channeled, directed, moved along paths designed by engineers to remove it from the urban environment as quickly as possible. Storm drains carry this water into underground pipes, storm sewers that run beneath streets, collecting runoff from thousands of drain inlets. The water flows through this pipe network, joining with water from other parts of the city, accumulating volume, moving toward outfalls that release it into rivers or lakes or the ocean. In some cities, storm sewers are separate from sanitary sewers. In older cities, they're combined, which can cause problems during heavy rain when the combined volume overwhelms treatment plants. The speed of urban runoff is striking. Rain can fall on a city and within minutes create significant flows in gutters and drains. There is no soil to absorb and slow the water, no vegetation to intercept it. It all becomes runoff immediately. This rapid response means urban streams and rivers can flood very quickly during heavy rain. Flash floods triggered by intense but brief downpours. Water moving so fast that it rises dangerously within an hour of rain beginning. Urban runoff also picks up pollutants. Rain falls clean from the sky, slightly acidic from dissolved seal, but otherwise pure. The first rain after a dry period washes accumulated pollutants from surfaces, oil drips from cars, tire particles, metals from brake pads, trash, chemicals, everything that accumulates on pavement. This first flush is particularly dirty, carrying concentrated pollutants into storm drains and eventually into natural water bodies. Rain becomes polluted by the city it falls through, arriving at the river or lake carrying the city's contamination. Green infrastructure, rain gardens, permeable pavements, green roofs, bioswales. Attempts to slow runoff, allow infiltration, treat pollutants naturally. These systems intercept rain before it enters storm drains, giving it paths to soak into soil or evaporate or be taken up by plants. It is an effort to make cities behave more like natural landscapes where rain is concerned. But in most urban areas, rain still means runoff. The drop falls, lands on hard surface, flows downhill, enters the engineered drainage system, and is removed from the city as efficiently as possible. The city sheds rain rather than absorbing it, treating precipitation as something to be channeled away rather than something to be captured and used. Urban rain becomes urban runoff. And from the drop's perspective, it is a fast, straight path from sky to storm drain to river, completing its journey through the city in minutes or hours, rather than the days or weeks it might spend infiltrating through soil. Once rain lands, its journey branches. What was one drop falling one path now becomes multiple possibilities, multiple futures, depending on where and how it landed. The water cycle is a simple circle. It is a web of paths, with each drop potentially taking different routes through the system. Some water evaporates almost immediately. Rain on hot pavement can vaporize within minutes as the sun comes out after the storm. The drop never soaks in, never joins a stream. It just returns to atmosphere, becoming vapor again, possibly condensing into a cloud again later the same day. This is especially common in arid regions, where intense sun and low humidity quickly evaporate surface water. Some water becomes runoff. It flows across surfaces, joins with other drops in rills and rivulets, becomes part of small streams that join larger streams that join rivers. This water is moving quickly toward the ocean or a lake, traveling on the surface, visible, flowing downhill under gravity. Pull. It might reach the ocean within days or weeks, depending on how far it has to travel and how fast the rivers flow. Some water infiltrates and becomes soil moisture. It soaks into the ground, spreads through the soil, but remains in the root zone where plants can access it. This water might stay in the soil for days or weeks before being absorbed by roots, pulled into plants, and transpired back to atmosphere through leaves. It completes a local loop, rain to soil to plant to air to rain again, all within a small geographic area. Some water infiltrates deeply and becomes groundwater. It percolates past the root zone, keeps moving downward, reaches the saturated zone where it joins vast underground water stores. This water moves very slowly, maybe a few feet per year through dense rock, faster through permeable layers. It might remain underground for decades, centuries, even millennia before emerging at a spring or being pumped from a well. This is ancient water, water that left the surface long ago and will remain hidden until something brings it back up. Some water is intercepted by plants before reaching ground. It lands on leaves and either evaporates directly from the leaf surface or drips from the leaves to lower leaves to ground. Forests intercept a significant fraction of rain. Sometimes 20 to 30% of rainfall never reaches the ground beneath trees, instead evaporating from canopy surfaces. The water returns to atmosphere without ever becoming soil moisture, and some water lands on animals. A drop strikes a deer's back and rolls off, or soaks into fur before evaporating. It lands on a bird and beads up on feathers. It strikes a human and either soaks into clothing, evaporates from skin, or drips to the ground. These are tiny fractions of total rainfall, but they re-part of the branching pattern. Every rainstorm divides into these various paths. Some water takes each route, the proportions depending on where the rain falls and what conditions exist at the surface. Desert rain mostly evaporates or becomes flash flood runoff. Forest rain mostly infiltrates or is intercepted by canopy. Urban rain mostly becomes runoff. The cycle branches, water dispersing through multiple pathways, all eventually returning to atmosphere or ocean, but each taking its own route and timeline. Deep in the soil, a root waits. It is part of a plant, maybe a tree, maybe grass, maybe a crop. and it has been waiting through dry days for rain. The soil around it has been drying slowly, water draining deeper or being taken up by the plant itself, soil moisture decreasing as evapotranspiration continues, but no new water arrives. The root is still alive, still functional but stressed. The plant above ground shows it wilting slightly, leaves drooping, growth slowed. Then rain falls. The drops strike the soil surface far above the root's location, and infiltration begins. Water moves downward through the soil, following pore spaces, pulled by gravity and capillary action, spreading through the soil profile. Within hours, the moisture wave reaches the root's depth. The soil around the root transitions from relatively dry to moist. The root senses this. Not through consciousness, it has none, but through physical changes in the soil's water potential. When soil is dry, water is held tightly to soil particles by adhesive forces, and the energy required to pull that water free is high. When soil is wet, water is held less tightly, more easily accessible. The root can absorb it more readily. Water moves from soil into root through osmosis. Water molecules crossing the root's cell membranes from high water potential, wet soil to low water potential. Inside root cells, where water is less concentrated due to dissolved sugars and minerals, the root doesn't actively pull water. Water moves because of the concentration gradient. But the effect is the same. Water enters the root, begins moving up through the plant's vascular system, the xylem pulled ultimately by evaporation from leaves at the top of the plant. Within hours or days, depending on plant size, the rain that fell on soil is being transpired from leaves. The water molecule that was rain, that soaked into soil, that entered a root, it travels up the stem, into branches, into a leaf, into a stomata, a tiny pore on the leaf surface, and exits as vapor. It is back in atmosphere, ready to potentially become rain again. The plant responds visibly to rain. Leaves that were drooping become turgid again. Cells filled with water, internal pressure restored. Growth resumes. Cell division and expansion both require water. New leaves might begin forming within days of rain. Flowers might open. Fruits might swell. The plant uses the water for almost everything it does. Photosynthesis requires water as a raw material. Cell expansion requires water for turgor pressure. Cooling requires water for evaporative temperature control. For the plant, rain is life, not metaphorically. Without rain or irrigation, which is just rain's human substitute, terrestrial plants can't survive. They're made of water, they use water constantly, and they need water to be replenished regularly. Rain is the replenishment, the answer to the waiting, the end of drought stress. When rain arrives after dry weeks, it is not just water soaking into soil, it is the difference between plant survival and plant death, between growth and dormancy, between the ecosystem functioning and the ecosystem shutting down. A forest in rain is a massive water processing system. The canopy intercepts rain-first trees' leaves and branches, catching drops before they reach ground. Some drops stick to leaf surfaces, held by surface tension, eventually evaporating without ever reaching soil. Others drip from leaf to leaf, losing energy in each impact, finally falling gently to the forest floor rather than striking it with full force. Some rain becomes stem flow, water that runs down tree trunks. Branches channel water toward the trunk, and the trunk's vertical surface guides it downward to the base. This concentrates water near the trunk, where the tree's major roots are located. It is an efficient system. The tree's architecture funnels water toward its own root system. After heavy rain, you can see this trunks are wet and dark with flowing water, while the ground between trees might be relatively dry because the canopy sheltered it. The forest floor is designed to absorb rain. Layers of leaf litter, decomposing organic matter, create a spongy surface that soaks up water readily. The soil beneath is usually rich in organic content, porous, full of root channels and earthworm burrows and other structures that allow rapid infiltration. Forest soil might absorb several inches of rain without generating much runoff, storing it in the soil profile where roots throughout the forest can access it. Trees use enormous amounts of water. A single large tree on a summer day might transpire hundreds of gallons, pulling that water from soil through roots, up through the trunk, out through leaves. Multiply this by all the trees in a forest, and the total water use is staggering. A forest is constantly moving water from soil to air, acting as a wick that pulls groundwater upward and releases it as vapor. Rain replenishes this system, replacing the water being constantly transpired. Forests also create rain, in a sense. The water they transpire increases atmospheric humidity, making clouds more likely to form. This is especially notable in tropical rainforests, where transpiration is so intense that much of the rain is actually recycled. Water falls, is absorbed by trees, is transpired, forms clouds, falls again, repeating in a local cycle. Cut down the forest, and rainfall patterns change because this recycling mechanism is broken. Rain in forests also feeds streams. The water that infiltrates beyond the root zone continues deeper, moving slowly through soil and rock, eventually emerging at springs or seeping into stream channels. Most forest streams during dry periods are fed by this groundwater, water that fell as rain weeks or months earlier, infiltrated, moved laterally underground, and is now emerging to maintain stream flow. Heavy rain adds surface runoff too, but the base flow is groundwater, which is really just old rain still making its way through the hydrologic system. The relationship between forest and rain is reciprocal. Rain makes forests possible by providing the water trees need. Forests modify how rain behaves, slowing it, spreading it, holding it in soil, releasing it gradually. Remove the forest, and rain becomes flashier. More immediate runoff, less infiltration, more erosion, less steady stream flow. The forest mediates rain's effects, turning pulses of precipitation into steady availability of water over time. In the desert, rain is event. In wetter climates, rain is common, expected, almost boring in its regularity. But in deserts, rain is rare, dramatic, transformative. When rain finally falls in a desert, everything responds. Life that has been dormant erupts into activity. The landscape changes within hours. Rain in the desert is miracle and chaos together. The ground is hard when rain arrives, baked by sun, dried deeply. Often crusted, desert soil resists infiltration initially. The first rain might puddle on the surface, unable to soak in immediately. But as the ground saturates, infiltration improves. Water begins soaking in, moving through cracks in the dry soil, spreading laterally, reaching depths that have been dry for months or years. Seeds respond almost immediately. Desert annual plants, wildflowers, grasses have seeds that can remain dormant in soil for years, waiting for the precise signal of rain. When water reaches them, they germinate within hours or days. Within a week, the desert might be carpeted in green shoots. Within 2 weeks, flowers sudden explosions of color in a landscape that was brown and bare days earlier. These plants race through their entire life cycle in the brief window. While water is available, flowering and setting seed within weeks before the soil dries again. Animals respond too. Frogs that have been buried underground, dormant, waiting. They emerge when rain creates temporary pools. Desert toads spend most of their lives underground in a state of estivation, a dormancy similar to hibernation. But when rain creates puddles, they dig out, emerge, immediately begin breeding. They might have just days or weeks before the pools evaporate. They breed frantically, lay eggs, and tadpoles must complete metamorphosis before the water disappears. It is extreme life history strategy, everything compressed into the brief window of water availability. Insects emerge from eggs that have been waiting in dry streams. Fairy shrimp, tadpole shrimp, ancient crustaceans whose eggs can survive decades of desiccation, hatching within hours of water arrival. They swim in temporary pools, feeding on bacteria and algae, growing rapidly, reproducing, creating the next generation of drought-resistant eggs before the pool dries up again. The desert smells different after rain. There is a distinctive scent called petrichor, the smell of rain on dry earth, caused by oils released from plants during dry periods being dispersed by rain, plus geosmin, a compound produced by soil bacteria that creates that earthy smell. In deserts, this scent is intense because the dry periods are so long and the contrast so sharp. Flash floods are common in desert rain because the soil can't absorb water fast enough, and because desert landscapes often have sparse vegetation to slow runoff. Even modest rain can create powerful flows in normally dry washes and canyons. Water rushes downhill, brown with suspended sediment, carrying debris, reshaping the landscape, sometimes dangerously strong. Desert rain is precious. Every drop matters. Life has adapted to survive without it for long periods. But rain is the trigger, the catalyst, the moment when the desert comes alive. It is feast after prolonged famine, abundance after scarcity, the brief window when desert life blooms before returning to patient waiting. Every river was rain once, not just some of the water in rivers, all of it. Rivers are collections of raindrops, aggregated over vast areas, concentrated into channels, flowing toward the sea. Understanding rivers means understanding how rain accumulates. It begins with individual drops falling on slopes. They don't immediately form rivers. First, they form tiny rills, miniature channels just millimeters wide, where water flows downhill in thin sheets. Multiple rills merge into rivulets, slightly larger channels, maybe centimeters wide, cutting small grooves into hillsides. Rivulets merge into brooks, named now, identifiable as flowing water, perhaps a meter wide, moving visibly downhill. Brooks merge into creeks. Creeks merge into streams. Streams merge into rivers. Each merger adds water volume, increases flow rate, carves deeper channels. The network looks like a tree in reverse. Tiny branches converging into larger branches, converging into the trunk. This pattern is called a drainage basin or watershed. All the land area that contributes rain to a particular river system. Large rivers collect rain from enormous areas. The Mississippi River's watershed is about 1.2 million square miles, roughly 40% of the contiguous United States. Every raindrop falling in this vast area, if it does evaporate or get used by plants, eventually flows to the Mississippi and down to the Gulf of Mexico. The Amazon's watershed is even larger, about 2.7 million square miles, collecting rain from much of South America. The time from rainfall to river flow varies enormously. Rain falling near a river channel might reach the river within hours. Rain falling far up in the watershed might take days or weeks to flow through tributaries and reach the main river. Rain that infiltrates and becomes groundwater might take months or years, eventually emerging at springs that feed stream headwaters. This is why rivers keep flowing during dry periods. They not just carrying current rain, they recarrying rain that fell weeks or months ago. Water that has been slowly making its way through the drainage network. Groundwater that continues seeping into stream channels, even when it is not raining. The river integrates precipitation over time, smoothing out the pulses into more steady flow. Heavy rain causes floods. When rain falls faster than the drainage network can accommodate, water backs up, rivers rise above their banks, floodplains fill. This is natural and necessary. Floodplains exist because they flood, and ecosystems in floodplains depend on periodic inundation. But floods can be destructive to human infrastructure, built in areas that should flood, but that we tried to protect. Rivers are Earth's circulatory system. They move water from where it falls, distributed across vast land areas, to where it collects, the ocean. They the arteries carrying water back to the sea, completing the cycle, returning rain to the source of evaporation, so the cycle can continue. Every river is rain's journey becoming visible, drops becoming flow, precipitation becoming current. Following a river downstream is following rain's path home. From mountain headwaters where streams begin, through foothills where tributaries merge, across plains where rivers widen and slow, to deltas where fresh water meets salt. Every inch of this journey is rain in motion, gravity pulling it inexorably toward sea level. Human civilization is built on rain's reliability, not literally. We don't build structures from rain, but functionally. Our societies depend on the assumption that rain will fall in predictable amounts, in roughly expected places, with reasonable consistency. When rain fails or becomes too extreme, civilizations strain. Agriculture is the most obvious dependence. Crops need water, and most cropland in the world is rain-fed, not irrigated. Farmers plant seeds and hope for rain at appropriate times. Too little rain means crop failure, food shortage, potentially famine. Too much rain means flooding, rotting crops, also failure. The entire global food system depends on rain falling in amounts that allow crops to grow enough, but not too much. Timed with growing seasons, distributed across the agricultural regions that feed billions. Even irrigated agriculture depends on rain, just less directly. Irrigation water comes from rivers or groundwater, both of which are fed by rain. If rain fails over several years, rivers run low, aquifers drop, irrigation becomes unsustainable. The famous aquifer depletion happening in places like California's Central Valley or India's Punjab, that is rain dependence, showing itself indirectly. We're using groundwater faster than rain replenishes it, borrowing from storage that took centuries to accumulate. Drinking water depends on rain. Municipal water supplies come from rivers, lakes, or aquifers, all fed by precipitation. Cities exist where they do partly because there is adequate water supply nearby. Cities in arid regions like Los Angeles or Phoenix survive by importing water from distant sources. But those sources are still rain-fed. The water had to fall somewhere, accumulate somewhere, before it could be moved. No rain somewhere means no water for cities that depend on that somewhere. Hydroelectric power is captured rain energy. The electricity generated by dams is really solar energy captured by the water cycle. Sun evaporates water. Water rises, falls as rain in mountains, accumulates in reservoirs, flows through turbines, generates power. Drought affects not just water supply but energy supply for regions dependent on hydropower. The water cycle is an energy transfer system, and we've learned to tap into it. Industry depends on water, which depends on rain. Cooling systems for power plants, processing water for manufacturing, semiconductor production, these require enormous water quantities. Industrial civilization's thirst is vast, and rain is the only source that replenishes what we use. Humans are one species among millions that depend on rain, but we're unique in how consciously we manage that dependence. We build reservoirs to store rain for later use. We drill wells to access ancient rain trapped underground. We plan cities and farms and industries around expected rainfall patterns. When those patterns change, when droughts last longer than expected or rains become more intense, our systems strain because they're designed for the old normal, not the new reality. Rain isn't just weather to us. It is infrastructure's foundation, economy's precondition, civilization's enabler. We rarely think about it in these terms until it fails, until drought reveals how completely we depend on the cycle continuing, on clouds forming, on rain falling in amounts and timing that allow everything we've built to function. Earth's water cycle exists in a remarkable balance, not a static balance. The amount of rain varies by location and season and year, but an overall balance that keeps the system stable enough for complex life to thrive. Too much rain everywhere, and we'd have a water world with minimal land. Too little, and we'd have a desert planet. The actual distribution is in between, creating diverse environments where different life strategies succeed. The amount of rain in any location represents a balance between evaporation and precipitation. Places where precipitation exceeds evaporation are wet rainforests, temperate forests, wetlands. Places where evaporation exceeds precipitation are dry deserts, arid grasslands. The difference determines ecosystem type, which determines what species live there, which determines the character of the landscape. This balance is maintained by global atmospheric circulation. Trade winds, jet streams, monsoons, these large-scale wind patterns move moisture from oceans to continents, from wet regions to dry regions, distributing rain in patterns that are chaotic on short timescales, but predictable on long timescales. The pattern is complex but not random. We can predict that the tropics will be wet, that rain shadows will be dry, that monsoon regions will have seasonal deluges. Too much rain causes problems even in wet-adapted ecosystems. Sustained flooding kills plants that can't tolerate waterlogged soil. Excessive erosion washes away topsoil. Landslides occur when slopes become saturated. Even rainforests, adapted to high rainfall, can be damaged by rainfall extremes beyond what they're adapted to. Too little rain is obviously problematic. Drought stresses all life forms that depend on regular water. Plants wilt, then die. Animals must migrate to where water still exists or die. Streams dry up, aquifers drop. The entire ecosystem enters crisis mode. Prolonged drought can shift ecosystems to new states. Forests becoming grasslands, grasslands becoming desert. If the dry period lasts long enough, the Goldilocks zone for rain is surprisingly wide. Life has adapted to exist across a huge range of rainfall conditions, from deserts with less than an inch annually to rainforests with over 400 inches. But each ecosystem is adapted to its local normal. Change that normal make a desert wetter or a rainforest drier, and the ecosystem can't simply adjust. The species present are selected for the existing regime. Change the regime and different species are needed, requiring migration or extinction and replacement. Human civilizations add another layer of balance requirements. We need rain to be not just adequate but predictable. Agricultural societies plant crops expecting rain at certain times. Urban water systems are designed for expected supply levels. Energy systems assume specific river flows. When rain's patterns change, more variable, more extreme, different timing, these systems designed for the old patterns struggle to cope. The balance isn't automatic or guaranteed. Earth's climate has shifted dramatically in the past. Ice ages with completely different rainfall patterns, warm periods with different distributions. The current balance is just the current balance, stable on timescales of decades or centuries, but not permanent on geological timescales. And now, with human influence on climate, the balance is shifting again, faster than in the recent past, testing the adaptability of ecosystems and civilizations, built assuming the balance would remain stable. Imagine Earth 4 billion years ago. It is a young planet, barely 500 million years old, still hot from its formation. The surface is mostly molten rock, volcanoes erupting constantly, the atmosphere thick with water vapor and carbon dioxide and other gases released from the interior. There is no life yet. Conditions are too extreme, too chaotic. The planet is still becoming what it will be. As Earth gradually cools, a threshold is approached. The surface temperature drops below water's boiling point. Suddenly, or rather, over centuries or millennia, water vapor in the atmosphere begins condensing. Clouds form for the first time in Earth's history. The sky fills with gray masses of suspended droplets, covering the planet in a thick layer, and then it rains. The first rain in Earth's history drops fall on barren rock, on land that has never known moisture, on surfaces hot enough that the first drops probably vaporize on contact, but more rain keeps falling. The clouds are thick, the atmosphere supersaturated with vapor. It rains continuously, perhaps for thousands of years, a planetary deluge that doesn't stop. This rain creates the oceans. Every ocean on Earth, Pacific, Atlantic, Indian, Arctic, Southern, formed from this ancient rainfall. Water that had been locked in minerals during Earth's formation released as vapor through volcanism, condensed and fell and accumulated in low-lying areas. The first puddles became the first lakes, became the first seas, became the oceans that now cover 70% of Earth's surface. The rain was probably acidic. Carbon dioxide dissolved in raindrops, creating carbonic acid, the same process that makes modern rain slightly acidic. This acidic rain began dissolving minerals from rock surfaces, a chemical weathering process that has continued for 4 billion years, shaping the planet's surface chemistry. The first rain cooled the planet. The heat capacity of water is enormous. Water absorbs and releases heat slowly. As oceans accumulated, they became thermal reservoirs, moderating temperature extremes, creating a more stable thermal environment. The planet's climate system began developing, driven by water's presence and movement. There were no rivers yet. Rivers require erosion to carve channels, and erosion requires time. But runoff existed, water flowing from higher elevations to lower ones, seeking sea level, finding the most direct path down. This runoff began the process of erosion, wearing away rock, carving the first valleys, creating the landscape patterns we still see today. For millions of years, rain fell continuously. The oceans filled. The atmosphere cleared. Water vapor condensed and fell, leaving behind a thinner atmosphere dominated by nitrogen and carbon dioxide. Eventually, equilibrium was reached. Evaporation balanced precipitation. The oceans reached their current volume, or close to it, varying over geological time with ice ages and warm periods, but never deviating drastically. This first rain was formative. It created the conditions necessary for life's emergence: liquid water at the surface, stable temperatures, dissolved minerals. Without rain, Earth would be dry like Mars or Venus, incapable of supporting life as we know it. Rain was the process that made Earth habitable, that transitioned it from a hot ball of rock to a water world where life could begin. And once the oceans existed, the water cycle began. Evaporation from ocean surfaces, condensation in clouds, precipitation as rain, collection in oceans again. The cycle has continued ever since, interrupted only briefly during ice ages, when much precipitation fell as snow and accumulated in ice sheets, rather than returning immediately to oceans. But the cycle itself has been continuous for 4 billion years, the same water, cycling repeatedly, falling as rain countless times. Each rainstorm, a repetition of that first ancient deluge. Over billions of years, rain has reshaped Earth's surface more than any other single process. Not dramatically. Rain doesn't carve canyons quickly or move mountains visibly. But slowly, persistently, rain wears away rock, transports sediment, and sculpts landscapes grain by grain, drop by drop. The mechanism is simple. Water physically and chemically breaks down rock. Physical weathering happens when water enters cracks, freezes, expands, and fractures rock apart. Chemical weathering happens when acidic rainwater dissolves minerals, particularly carbonates like limestone, but even resistant rocks, like granite, slowly decompose under rain's patient assault. The Grand Canyon is fundamentally a rain sculpture. Yes, the Colorado River carved it, but the river is just accumulated rain, thousands of years of precipitation collected in the Rocky Mountains, flowing through the canyon, grinding away rock with sediment carried in the water. The canyon wouldn't exist without rain to feed the river, without runoff to carry sediment, without rain directly weathering the canyon walls. Mountains erode under rain's influence. The Himalayas, still rising due to tectonic forces, are simultaneously being worn down by rain. Water runs off steep slopes, carrying rock particles, cutting channels, causing landslides. The mountains rise about 5 millimeters per year, but erode almost as fast. Without erosion, mountains would be much taller. Rain limits how high mountains can grow by constantly wearing them away. Coastlines are shaped partly by rain. Cliffs erode as rainwater seeps into rock, weakens it, causes chunks to fall. River sediment, all of it transported by rain-fed streams, builds deltas where rivers meet oceans. The shape of continents at their edges is determined partly by how rain moves sediment from interior to coast. Deserts exist partly because of rain's absence, but even deserts are sculpted by occasional rain. Flash floods in desert canyons move enormous volumes of rock and sediment in hours, carving arroyos and badlands. Desert landscapes are rain-carved, just by infrequent but intense rain rather than constant precipitation. Agricultural valleys like the Central Valley of California, the Midwest's prairies, river valleys worldwide. These exist because rain created them. Rivers deposited sediment, eroded from mountains, building flat, fertile valleys. The richest agricultural land is often alluvial soil sediment deposited by rivers, which are really just rain in motion. Even subtle landscapes show rain's influence. Hill slopes are shaped by the balance between uplift tectonic forces, raising land, and erosion, rain it down. The slope angle of any hill represents the angle where erosion exactly balances uplift, steeper, and erosion dominates. Gentler, and uplift isn't fully balanced. Rain determines this balance through how effectively it erodes. On a planetary scale, rain has transferred rock from continents to ocean floors. Over billions of years, entire mountain ranges have been eroded, and their sediment carried to sea, building up thick layers on ocean floors. This sediment eventually gets subducted, melted, and returned to continents through volcanism. But the transport mechanism is rain, weathering rock, moving sediment, carrying continents to oceans, piece by tiny piece. Earth's surface is temporary. Rain ensures this. Every feature is being worn away, however slowly. The only constant is change, driven by water, falling from the sky. Soil seems basic, mundane. It is just dirt, the brown stuff covering ground. But soil is remarkable. It is a mixture of mineral particles, organic matter, water, air, and billions of living organisms, all arranged in structured layers that took centuries or millennia to develop. And rain is fundamental to soil's existence. Soil begins with rock, parent material, usually bedrock or loose mineral deposits, is the starting point. Rain begins breaking this material down through physical and chemical weathering. Cracks fill with water, freeze, thaw cycles, fracture rock. Acids dissolve minerals. Rock becomes smaller pieces. Boulders become cobbles, become pebbles, become sand, silt, clay. This is mineral weathering, and rain drives it. But mineral particles alone aren't soil. True soil requires organic matter, decomposed plant and animal material that gives soil its dark color and fertility. Rain enables the plants that provide this organic matter. Without rain, vegetation would not exist to create the organic inputs that distinguish soil from mere weathered rock. Rain also moves soil components vertically and horizontally. Percolating rainwater dissolves minerals from upper layers and deposits them lower, creating distinct soil horizons. The A horizon rich in organic matter, the B horizon, where minerals accumulate, the C horizon of partially weathered parent material. This vertical differentiation is caused by rainwater leaching and depositing materials, creating structure. Earthworms and other soil organisms depend on adequate moisture, not too wet, not too dry. These organisms mix soil, creating pore spaces, breaking down organic matter, producing the granular structure that makes soil functional for plant growth. Rain maintains the moisture levels that allow these organisms to thrive. Soil formation is slow. In temperate climates, it might take 500 years to form an inch of topsoil. In tropical climates with intense rain, weathering is faster, but so is erosion, and rain can actually erode soil away faster than it forms. If vegetation is removed, the balance between soil formation and soil loss is partly determined by rainfall intensity and frequency. Different rainfall regimes create different soil types. Tropical high rainfall areas develop laterite. Soils highly weathered, leached of nutrients, often red from iron oxides that resist dissolution. Temperate moderate rainfall areas develop rich soils with good organic content. Arid low rainfall areas develop thin soils, often with salt accumulations near the surface, because there is not enough rain to leach salts away. Without rain, soil would be extremely thin, just a thin weathering rind on rock, no organic content, no developed horizons, no fertility. The deep, rich soils we depend on for agriculture exist only because rain has been falling consistently for thousands of years, weathering rock, supporting vegetation, moving materials, enabling the complex processes that transform rock and organic matter into the structured material we call soil. Soil is accumulated rain. In a sense, its existence represents thousands of years of precipitation supporting the physical, chemical, and biological processes of soil development. Every handful of earth contains molecules that have been rained countless times, that cycled through plants and organisms, that dissolved minerals, and moved through soil horizons. Soil is where rain becomes solid, where the water cycle creates something permanent from its continuous flow. The question of life's origin is still debated, but water's role is unquestioned. Life as we know it requires liquid water. Every biochemical process in living cells happens in aqueous solution. The molecules of life proteins, nucleic acids, carbohydrates, lipids need water to function. Life is fundamentally aqueous chemistry. Rain created and maintained the conditions for life's emergence. Once Earth cooled enough for liquid water to persist, pools and oceans existed, where the chemistry of life could begin. But how did organic molecules concentrate enough to interact and eventually self-organize into living systems? Rain might have helped. One hypothesis involves tidal pools or rain pools, small bodies of water that repeatedly evaporate and refill. Each evaporation concentrates whatever organic molecules are dissolved in the water. Add new rain, add new molecules from atmospheric chemistry or delivered by meteors, evaporate again. This cycle creates opportunities for concentrated chemistry, for molecules to interact at high concentrations, for complex compounds to form. Rain also cycles. Volcanic gases released into the atmosphere dissolve in rain, fall on surfaces, participate in surface chemistry. Some products evaporate back to atmosphere. This cycling might have been crucial for prebiotic chemistry, providing a mechanism to concentrate and distribute organic molecules across the planet's surface. Once life existed, rain became essential for its continued existence and spread. The first life was aquatic, but eventually life colonized land. This required adaptations to prevent desiccation, which required reliable rain. Land plants need water for photosynthesis, for cell turgor, for nutrient transport. They exist only because rain provides water regularly enough for survival. Rain enabled the spread of terrestrial life. Spores and seeds can disperse through air, but they need rain to germinate. Amphibians need water for reproduction. Even insects, which are relatively drought-resistant, depend on vegetation that depends on rain. The entire terrestrial biosphere is rain-dependent, directly or indirectly. Evolution has been shaped by rain patterns. Species adapt to local rainfall regimes, drought-tolerant plants in arid regions, moisture-loving plants where rain is abundant. Annual plants time their life cycles to rainy seasons. Animals migrate to track rainfall and the vegetation it supports. Evolutionary pressures related to water availability have shaped much of life's diversity. Rain might have even influenced the evolution of intelligence. Human evolution occurred in Africa during a period of high climate variability, including changes in rainfall patterns. Some theories suggest that climate variability forcing adaptation to changing conditions drove the evolution of cognitive flexibility and problem-solving abilities. Rain patterns, by determining food availability and habitat suitability, might have shaped human evolution. Without rain, Earth's life would be very different, probably just marine life. No terrestrial ecosystems, no land plants or animals. The diversity we see on land exists because rain made land habitable, because the water cycle delivers water to elevated regions, because precipitation supports ecosystems far from oceans. Rain isn't just necessary for life's existence. It shaped life's evolution, determined where life could live, enabled the complexity we see today. Earth's rainfall patterns haven't always been as they are now. Climate has varied dramatically over geological time, and with it, where and how much rain fell. Reconstructing ancient climates reveals that rain's distribution is not fixed. It shifts with global conditions, creating periods of wet and dry that lasted millennia. During ice ages, global rainfall patterns were very different. More water was locked in ice sheets, meaning less was available to evaporate and form rain. Overall, the planet was drier, but some regions that are currently dry were wet during ice ages. The Sahara Desert had lakes and rivers during some glacial periods, supported by rainfall from storm tracks that no longer exist in those locations. The Sahara's wet periods, called African humid periods, occurred when Earth's orbital variations changed the intensity of monsoon rains. These happened several times in the past 100,000 years, most recently ending around 5,500 years ago. During humid periods, the Sahara was grassland and savanna, supporting large animals and human populations. When rain patterns shifted, the region dried, the desert expanded, and populations had to migrate or adapt. Ancient coal deposits tell stories of ancient rain. Coal forms from plant material accumulated in swamps, environments that require high rainfall and poor drainage. The vast coal beds of the Carboniferous period, about 300 million years ago, indicate that much of the land was wet tropical swamp, rainier than most modern environments. Global rainfall distribution was different, possibly because continents were arranged differently and ocean currents distributed heat differently. Desertification of formerly wet regions isn't just recent. It has happened repeatedly through Earth's history. The petrified forest in Arizona preserves trees that grew in a wet climate 200 million years ago, when the region was near the equator and received tropical rainfall. Now, it is desert. The rain moved, not because the rocks moved though they did, with continental drift, but because global climate patterns shifted. Evidence of ancient rainfall is preserved in rocks. Limestone caves form where rainwater dissolves underground carbonate rock. Caves exist where it rained long enough for significant dissolution. Sedimentary patterns show where ancient rivers flowed, which indicates where rain fell to feed those rivers. Even the composition of ancient soils can indicate whether they formed under high or low rainfall. Ice cores from Antarctica and Greenland provide detailed records of past precipitation. The ice is accumulated snow, which is just frozen rain, and layers in the ice record how much snow fell each year going back hundreds of thousands of years. Analyzing these layers reveals that precipitation varied significantly, with some periods much wetter or drier than others. Understanding ancient climates helps us understand current changes. The climate system can exist in different states, each with different rainfall patterns. What is normal is really just the current configuration, and we know from the past that normal shifts. The patterns we built civilizations around, Mediterranean dry summers, monsoon seasons, temperate zone precipitation, aren't permanent. They've been different before and will be different again, either naturally or hastened by human influence on climate. There is a particular kind of rain that barely feels like rain at all, drizzle, mist, that finest precipitation that seems to hang in the air more than fall through it, where each drop is so small you can barely feel individual impacts. But stay outside long enough and you are thoroughly soaked. Drizzle drops are tiny, typically 0.2 to 0.5 millimeters in diameter, much smaller than the raindrops we've been following. At this size, they fall at walking pace, maybe 3 to 5 miles per hour. You could jog alongside drizzle and match its descent speed. This slow fall means drizzle takes a very long time to reach ground from even low clouds, and much of it evaporates during the descent unless the air is near saturation. Drizzle forms in shallow stratiform clouds, those flat, featureless gray layers that create overcast skies without drama. These clouds don't have strong updrafts or significant vertical development. They re-thin, maybe only a few hundred meters thick, so droplets don't spend much time inside them, don't have many opportunities to collide and grow. Most droplets remain cloud-sized, but some grow just large enough to fall as drizzle. The experience of drizzle is gentle, persistent, quiet. There is barely any sound. Drops are too small to make audible impacts, except on the most resonant surfaces. No splashing, no drumming, just a slow dampening. Everything gradually getting wetter without obvious precipitation. It is the rain you don't notice until you realize you are soaked. Mist is even finer, droplets so small they practically cloud at ground level. The line between heavy mist and light drizzle is blurry, more continuum than distinct categories. Mist reduces visibility more than it wets surfaces, though stay in it long enough, and surfaces do get damp. It is like walking through a cloud, which technically you are. Mist is just cloud that exists at surface level rather than overhead. Drizzle days have a particular mood. Gray, soft, muffled. Light is diffuse. Shadows are absent. Distances are hard to judge. Everything feels close, intimate, quiet. These aren't dramatic weather days. Nothing is going to happen suddenly. No thunderstorms developing, no shifts. Just steady gray, gentle dampness, hour after hour, sometimes lasting all day. Plants respond differently to drizzle than to rain. Large drops can physically damage delicate leaves, but drizzle is harmless, just slow hydration. Mosses and lichens thrive in drizzle. They can absorb water directly through their surfaces, and prolonged gentle wetness is perfect for them. Fungi fruit in drizzle weather, mushrooms appearing after days of damp. There is a geography to drizzle. Coastal areas get more. Marine air is humid. Clouds form at low altitude. Conditions favor stratus clouds and drizzle. The Pacific Northwest of North America is famous for drizzle, as are parts of the British Isles. It is part of the regional character, the climate personality. Locals don't use umbrellas for drizzle. It is too omnidirectional, too persistent, too much a part of the air itself, rather than something falling through air. Drizzle is rain in its gentlest form, precipitation at its most subtle. It is easy to dismiss as not quite rain, but it is real precipitation, real water cycling from cloud to ground, just in the smallest possible drops that can make the journey successfully. Summer rain is different. It is warm, sudden, dramatic. Clouds build vertically through the afternoon, towers of cumulus growing taller as sun-heated air rises powerfully. By late afternoon, some towers have grown into cumulonimbus, thunderheads, storm cells, monsters of clouds reaching 7 or 8 miles high, their tops flattening against the stratosphere. Then it opens up. The rain doesn't start gently. It begins immediately at full intensity. Large drops, falling fast, striking with force. This is rain that makes noise, that splashes visibly, that overwhelms gutters within minutes, that sends people running for shelter. The sound on roofs is almost violent, a sustained roar rather than gentle pattering. The drops are big 3, 4, sometimes 5 millimeters, approaching the maximum size drops can achieve before breaking apart. They sting slightly when they hit bare skin. They create dramatic splashes when they strike pavement, each impact sending up a tiny crown of water that catches light momentarily before falling back. Within seconds of the rain starting, every surface is wet. Within a minute, puddles are forming. Within 5 minutes, streets might be running with water. The rain is warm. The drops formed in high cold clouds, but they fell through miles of warm summer air and absorbed heat along the way. When they strike your skin, they don't chill. They might even feel pleasant, like a warm shower. This is rain you can enjoy being in, rain that is refreshing rather than miserable, assuming you don't mind being soaked. The intensity rarely lasts long. Summer thunderstorms are brief 15 minutes, maybe 30, rarely more than an hour at any one location. The storm cell moves, carried by prevailing winds, so the heavy rain follows a track across the landscape. If you're in the path, you get drenched. If you're a mile away, you might see the storm but get no rain at all. After the storm passes, the world changes. Dust has been washed from leaves and surfaces. The air smells clean, with that distinctive petrichor of rain on hot earth. There is often a temperature drop 10 degrees or more, because the rain cooled the air and evaporation continues to cool surfaces. Humidity rises, but feels less oppressive because temperature dropped. Sunlight often breaks through shortly after the storm. This creates spectacular lighting, golden sun rays through gray clouds, rainbows forming in the clearing air, dramatic contrast between dark storm clouds and bright lit areas. These post-storm moments are some of the most beautiful weather phenomena. That specific summer storm aesthetic of rain-washed landscape under angled sunlight. This rain is erosive. Its intensity overwhelms soil's absorption capacity, creating runoff, even in areas with good soil. Water runs in sheets across slopes, cuts small channels, carries sediment. Flash floods in canyons and streams happen during these storms, quiet channels suddenly running with brown, debris-filled water, subsiding again within hours. Summer rain is weather as event, not background, not subtle, but dramatic, noticeable, memorable. You remember summer thunderstorms, where you were, whether you got caught in it, the sudden coolness and noise and intensity. This is rain with personality, rain that announces itself, rain that doesn't let you ignore it. In the tropics, rain is a daily fact. Not every single day, but close. Especially during rainy season, rain falls most afternoons with remarkable regularity. The pattern is predictable. Morning sunshine, building clouds by noon, rain by mid-afternoon, clearing by evening, day after day, week after week, month after month. The regularity comes from strong solar heating. Near the equator, sun is nearly overhead year, round, heating the surface intensely. This creates powerful convection, warm, humid air rising vigorously, forming towering cumulonimbus clouds every afternoon. These clouds produce rain. Heavy rain, then dissipate. The next morning, the cycle begins again. Tropical rain is warm. Drops might be 75 or 80 degrees Fahrenheit when they land, just slightly cooler than the air. Getting rained on in the tropics isn't uncomfortable from a temperature perspective. It is just wet. You can stand in tropical rain and not feel chilled, just progressively soaked. Some people continue outdoor activities during rain because it is warm enough to not be problematic. The quantity of rain is astounding. Tropical rainforests might receive 80 to 400 inches of rain annually. That is 6 to 30 feet of water if it didn't run off or evaporate. Even a modest tropical rainstorm might drop several inches in an afternoon. The ground never fully dries. Everything is perpetually damp, soil, vegetation. The air itself is humid, even when it is not raining. This constant moisture enables the rainforest ecosystem. Trees grow year-round because there is never a dry season limiting growth. Vegetation is lush, layered, competitive for light rather than water. Epiphytes, plants growing on other plants, thrive because air itself contains enough moisture for survival. Fungi and decomposers work continuously in the warm, wet conditions, recycling nutrients rapidly. Rivers in the tropics are enormous because they re-fed by such high rainfall. The Amazon, Congo rivers in Southeast Asia, these carry tremendous water volumes because their watersheds receive so much rain. The Amazon alone discharges about 7 million cubic feet of water. per second into the Atlantic, roughly 20% of all river water entering all oceans worldwide, from just one river system. That volume represents rain falling across the Amazon basin, accumulated and concentrated. Tropical rain has cultural impacts. Architecture adapts, steep roofs to shed water, covered walkways, buildings designed to stay cool and dry despite constant moisture. Daily rhythms adapt. Outdoor work happens during morning hours before afternoon rain. Agriculture uses crops that tolerate or even require high moisture. There is a certain monotony to tropical rain. Regularity. It is not dramatic like temperate zone storms. It is expected, routine, just part of the daily cycle. But the quantity and consistency are remarkable. Imagine experiencing 6 feet of water falling from the sky over a year, spread across hundreds of rainy afternoons. That is normal for tropical rainforests, a rainfall regime so abundant it seems excessive until you realize the ecosystem is built for exactly this amount, that less would stress it, that the entire structure depends on continuous water availability. Tropical rain shows what Earth's water cycle can produce at maximum intensity. Not necessarily larger individual drops, but more of them, more often, for longer, accumulating to totals that dwarf precipitation in temperate or dry regions. There is a particular misery to cold rain, not freezing rain. That is different, more dangerous, a coating of ice on everything. Just cold rain drops that are liquid, but barely. Temperature hovering just above freezing, wind pushing the rain sideways. Every exposed surface quickly chilled. Cold rain happens in autumn and early winter, in spring too, transitional seasons when temperature hovers near that boundary between rain and snow. The drops might be 34, 35, 36 degrees Fahrenheit. Just warm enough to remain liquid, just cold enough to be profoundly uncomfortable. This rain doesn't refresh, it chills, soaking through clothing, conducting heat away from your body, making you cold from outside. The formation of cold rain is interesting. Often it starts as snow high in the clouds, but falls through a layer of air slightly above freezing and melts during descent. By the time it reaches ground, it is liquid, but barely. It is recent. Snow still carrying coldness from its frozen phase. You can almost feel that it was ice moments ago. Cold rain makes everything harder. Hands become clumsy. Numb blasts fog and become useless. Visibility is poor. Gray sky, gray rain, gray landscape, everything monochrome and dim. Puddles are icy cold. Pavement feels slippery even when it is not frozen, just slick with cold water. This is weather that pushes you indoors, that makes outdoor activity unpleasant enough to avoid. For plants, cold rain is a challenge. It can freeze on surfaces if temperature drops overnight, creating ice coatings that damage cells. For crops not yet harvested, cold rain can be disastrous, freezing and damaging produce. Late autumn rain that turns to freezing rain can devastate fruit still on trees, cracking fruit as water inside freezes and expands. Cold rain has a harsh sound. Drops striking surfaces seem sharper, more distinct, less soft than warm rain. There is a particular acoustics to cold rain, maybe because surfaces are harder when cold, maybe because the rain itself is denser being colder, maybe just psychological association with the discomfort. Animals respond to cold rain by seeking shelter. Birds fluff feathers for insulation and huddle. Mammals seek cover, reducing activity until conditions improve. Insects essentially shut down. Metabolism slow in cold, and wet at cold is doubly stress-inducing. The landscape quiets during cold rain, life waiting it out rather than continuing through it. There is an aesthetic to cold rain, though gray skies, bare trees, brown landscape, everything reduced to essentials. A certain stark beauty in the bleakness. This is autumn's mood made manifest: decay, dormancy, the year ending. Cold rain feels appropriate to the season, fitting with falling leaves and shortening days and the approach of winter. The transition from cold rain to snow is something you can sometimes witness. Rain falls, temperature drops, and suddenly the drops are becoming sleet, pellets of ice, halfway between rain and snow. Then snow, large flakes, suddenly transforming the precipitation from liquid to solid, changing the storm's entire character. That transition moment, watching rain become snow, is a visible threshold being crossed. Water, S-phase change happening in real time as drops fall. Cold rain is rain at its limits. Precipitation barely maintaining liquid state. Threshold weather that could tip into snow with a degree or two of cooling. It is uncomfortable but temporary, a seasonal phenomenon that passes with either warming or freezing. Rain follows rhythms, not just random weather, but patterns that repeat annually, shaped by solar heating variations as Earth orbits the Sun. These rhythms create rainy seasons and dry seasons, summer storms and winter rains, predictable patterns that ecosystems and cultures adapt to. Monsoons are the most dramatic seasonal rain pattern. In South Asia, summer brings the southwest monsoon, months of heavy rain, starting in June, continuing through September, providing 70 to 80% of India's annual rainfall. The mechanism is differential heating. Land warms faster than ocean in summer, creating low pressure over land, pulling in moist ocean air, which rises and produces torrential rain. Entire agricultural systems depend on monsoon timing. Plant when monsoon arrives, harvest when it ends. Mediterranean climates have winter rain and summer drought. This pattern, wet, mild winters, hot, dry summers, is opposite to continental patterns and creates unique ecosystems adapted to summer aridity. Plants in Mediterranean climates are often sclerophyllous, tough, leaved to survive drought, and many are adapted to fire, which is common in dry summers. California, Mediterranean Basin, Chile, South Africa, Cape, all have this pattern. Mid-latitude continental regions often have summer rain maxima. Convective storms driven by solar heating produce most precipitation in summer months, though winter brings some rain or snow. The Great Plains of North America get most rain May through August, matching the growing season, conveniently timed for rain-fed agriculture. Tropical regions often have rainy and dry seasons rather than summer and winter. Rainfall follows the Intertropical Convergence Zone, TSCZ, a belt of convection that migrates north and south with seasons. When the ITC is overhead, it rains frequently. When it is far away, conditions are relatively dry. This creates distinct wet and dry periods in much of the tropics. These rhythms have shaped life profoundly. Deciduous trees shed leaves partly in response to seasonal water availability in some regions. Many animals breed during or just before rainy seasons, so offspring are born when food is abundant. Birds migrate tracking seasonal rain, following the greening that rain brings across continents. Human agricultural calendars are based on rainfall seasonality. Plant when rains begin, harvest before dry season, or before rains become excessive. Cultural festivals often relate to rain rhythms. Harvest festivals coincide with the end of rainy seasons. Prayers for rain mark the expected beginning of rainy seasons. New Year celebrations in some cultures coincide with rain patterns. Monsoon onset, spring rains, whatever marks the agricultural year's beginning. Climate change is disrupting these rhythms. Rainy seasons are starting later or earlier, lasting longer or shorter. The reliability is decreasing. What was predictable becomes uncertain. This disruption affects everything adapted to the old rhythms: ecosystems, agriculture, water supply planning. When a rhythm that is held for centuries changes, systems designed around that rhythm struggle. But for now, seasonality persists. You can still predict, broadly, when rain will fall in most regions. Farmers still plant by traditional calendars, with adjustments. Ecosystems still respond to seasonal cues, though sometimes imperfectly. The rhythm is changing, but hasn't broken yet, still providing enough pattern for adaptation, still creating the seasonal structure that shapes much of life on Earth's land surfaces. Not all locations are equal where rain is concerned. Some places get abundant precipitation while nearby regions stay dry. The distribution is complex, determined by geography, topography, wind patterns, ocean currents, creating enormous variation over surprisingly short distances. Rain shadows are the most dramatic example. When prevailing winds carry moist air toward mountains, the air is forced upward to pass over the range. As it rises, it cools, reaching its dew point, forming clouds and producing rain on the windward side of the mountains. But after crossing the peaks, the air descends, warms, and dries out. The leeward side of mountains gets little rain. The moisture was removed on the windward side. This creates a rain shadow. The Hawaiian Islands demonstrate this perfectly. The northeast sides of islands face prevailing trade winds and receive abundant rain, over 400 inches annually in some locations. But just 10 or 20 miles away on southwest sides, rainfall might be less than 20 inches annually, dry enough to be semi-arid, same islands, same climate zone. But mountains create dramatic rainfall differences. The western United States has extensive rain shadows. The Pacific Northwest coast is very wet. Olympic Peninsula gets 150+ inches annually, but the Cascades block moisture from continuing east. Eastern Washington and Oregon are much drier, receiving 10 to 20 inches annually in many locations. The Sierra Nevada creates an even more dramatic rain shadow, wet California coast and western Sierra, but Nevada immediately east is desert. One of the driest states in America. Rain shadows explain many of the world's deserts. The Atacama Desert in Chile is in the rain shadow of the Andes. The Gobi Desert is partly rain, shadowed by the Himalayas. Patagonia's eastern side is dry because the Andes wring out moisture from Pacific air before it reaches the east. Some locations are extremely wet not because they get more storms, but because they reposition to receive every storm's full rain potential. More Sinram, India, holds the record for wettest place on Earth. Average annual rainfall over 460 inches, 38 feet. It is positioned where monsoon air rises up steep slopes, producing extreme orographic rainfall. Conversely, some places are extremely dry. The Atacama Desert's core receives less than 0.04 inches annually. Some locations haven't received measurable rain in decades. This extreme aridity is due to multiple factors: rain shadow, cold ocean current offshore suppressing evaporation, atmospheric circulation patterns that bring sinking, drying air. These extremes show how localized rain can be. It is not just wet regions and dry regions. There are wet microclimates within dry regions, dry microclimates within wet regions. A particular valley might get twice the rain of a valley 5 miles away because of how wind interacts with topography. A hillside facing one direction might support rainforest while the opposite hillside is grassland. Understanding these patterns matters for agriculture, water supply, ecosystem conservation. Knowing why rain falls where it does helps predict how climate change might redistribute it. If wind patterns shift, if mountain snowpack changes, if ocean temperatures alter, the patterns of rain could shift dramatically, creating winners and losers in the geographic lottery of precipitation. The rain you experience today falls in a different world than the rain your grandparents knew. The atmosphere is warmer, containing more water vapor, creating conditions for precipitation that differ subtly but measurably from the past. This isn't speculation, it is observed, measured, documented in rainfall records from thousands of stations worldwide, in flood records, in drought frequency, in the changing character of how rain falls. The basic pattern is, wet places are getting wetter, dry places getting drier. This sounds simple but captures a fundamental trend. Regions that already receive significant rainfall, tropics, mid-latitude storm tracts, are receiving more. Regions that were already dry, subtropics, rain shadow areas, are becoming drier. The distribution is becoming more extreme, less moderate, more variable. Why? Warmer air holds more water vapor. The atmosphere's capacity for moisture increases about 7% per degree Celsius of warming. A warmer atmosphere can load up with more vapor before becoming saturated, meaning when saturation is finally reached and clouds form, there is more water available to fall as rain. This creates potential for more intense individual precipitation events. But more intensity doesn't mean more total rain everywhere. In some regions, especially where rain was already sporadic, the longer dry periods between storms more than offset any increase in storm intensity. The rain becomes more concentrated in time and space, heavy when it falls, but falling less often, creating feast or famine hydrology. Data shows this is happening. Measurements of intense rainfall events, downpours that drop large amounts in short times, show they becoming more common in many regions. 1. Our rainfall records are being broken with increasing frequency. 100-year flood levels are being reached more often than once per century. The tail of the distribution, the extreme events, is getting fatter. Meanwhile, droughts are becoming more intense in drought-prone regions. Soil moisture is decreasing, groundwater levels dropping, vegetation stress increasing. This happens partly because higher temperatures increase evaporation rates, drying soil faster even if rainfall doesn't decrease much. The combination of less frequent rain and faster drying creates more severe drought conditions. There is geographic variation in how this plays out. The Mediterranean basin is drying, rain is becoming less frequent, droughts more common. The Asian monsoon region is seeing more intense rainfall events within the monsoon season, but also more variability in monsoon timing and intensity. North American Southwest is experiencing more severe droughts. The Pacific Northwest has seen increases in winter precipitation, but decreases in summer. These changes stress systems designed for the old rainfall patterns. Urban drainage systems are sized for historical rain intensities. More intense storms overwhelm them, causing flooding. Agricultural practices assume historical rainfall patterns. Changes in timing or intensity affect crop success. Water supply systems store water based on expected rainfall and snowpack. Changes in either create supply problems. Importantly, these changes are ongoing. We are not transitioning from one stable state to another. We are in a period of continuing change. Rain patterns will continue shifting as long as temperature continues rising. This creates uncertainty. We can plan infrastructure for a new normal because there isn't a new stable normal yet. Just continuing transition. The changes aren't catastrophic in the sense of sudden apocalypse. Rain still falls. Crops still grow. Life continues. But the margins have shifted. Things that used to work reliably now fail occasionally. Droughts that were rare become more common. Floods that were exceptional become less exceptional. It is death by 1,000 cuts, or rather stress by 1,000 small changes, each one manageable, but collectively representing a substantially altered hydrological environment. The mechanism is straightforward even if the implications are complex. Warmer atmosphere holds more water vapor before saturation. This is physics, not theory. The Clausius-Clapeyron relation describes exactly how saturation vapor pressure increases with temperature. Warm the air by 1 degree Celsius, and it can hold about 7% more water vapor. This is definite, measurable, unavoidable. More vapor means more precipitation potential. When air finally does saturate and condense, there is more water available to fall. Think of it like a larger bucket. Warm air is a bigger bucket for vapor, so when the bucket tips over, more pours out. Individual storms can produce more rainfall because they redrawing from a more vapor-rich atmosphere. But total rainfall is about more than just vapor content. It is also about circulation patterns, where and when air rises, creating conditions for clouds and rain. These patterns are changing too, in ways that are harder to predict than the basic thermodynamic vapor increase. Storm tracks are shifting. The jet stream, the high-altitude wind that steers mid-latitude storms, is becoming wavier, sometimes shifting north or south from historical paths. This moves rain toward some regions and away from others. The subtropical dry zones are expanding polluted in both hemispheres, bringing drier conditions to regions that were previously more moderate. Monsoons are changing in timing and intensity. The seasonal migration of the ITC's intertropical convergence zone is being affected by changing temperature patterns between land and ocean. Between hemispheres, monsoon onset might come later, ending earlier, or the peak intensity might increase while total duration decreases. These changes affect billions of people who depend on monsoon rain. Ocean temperatures matter enormously. Evaporation is faster over warmer water, so regions downwind of warming ocean areas receive more atmospheric moisture. But ocean currents are also changing. The Atlantic meridional overturning circulation may be slowing, which would affect European climate. El Niño and La Niña patterns might be changing in frequency or intensity, affecting global rainfall distributions. The complexity is that these factors interact. More vapor in the atmosphere affects cloud formation, which affects how much sunlight reaches the surface, which affects temperature patterns, which affects circulation, which affects where vapor gets transported and where rain falls. It is a coupled system with feedbacks, making specific regional predictions difficult, even though the overall direction, more intense but more variable, is clear. What is certain is the energy input. Adding heat to a system adds energy. The water cycle is an energy cycle. Solar energy evaporates water. Lifted water has potential energy. Falling water has kinetic energy. Evaporating water cools surfaces through energy absorption. More heat means more energy in this cycle, which means more vigorous cycling, faster evaporation, more intense precipitation, potentially more extreme events at both ends, flood and drought. The atmosphere is a heat engine, and we turned up the heat. Water is the working fluid in this engine, cycling from surface to air to surface, carrying energy with it. A hotter engine runs more intensely, and we re-observing exactly that. More intensity in the water cycle, more energy in precipitation systems, more extremes in both wet and dry directions. More intense precipitation sounds abstract. What does it actually mean on the ground? It means specific, observable changes in how rain falls and what effects it has. It means shifts from patterns that were predictable and manageable to patterns that are less predictable and sometimes overwhelming. More intense means shorter, harder bursts rather than gentle, steady rain. A storm that might have dropped 2 inches over 6 hours, historically might now drop the same 2 inches in 2 hours. Same total, but delivered faster, more concentrated in time. This changes everything about how water interacts with the landscape. When rain falls gently over hours, soil can absorb most of it. Infiltration rate is several times higher than rainfall rate, so water soaks in rather than running off. The ground has time to process the input. Streams rise gradually. Flooding is minimal. Erosion is limited. When the same amount falls in a third of the time, intensity exceeds infiltration capacity. Water puddles on the surface, then runs off. Soil can't absorb water fast enough, so much becomes surface runoff. Streams rise rapidly. Flash flooding becomes more likely. Erosion increases because flowing water carries sediment, and faster flow carries more sediment exponentially. Urban areas are particularly vulnerable to intensity changes. Storm drains are sized for specific rainfall intensities, typically something like a 2-inch-per-hour rate. When 5 inches falls in an hour, the system can't handle it. Streets flood, basements flood, combined sewer systems overflow. The infrastructure doesn't fail catastrophically, it just gets overwhelmed, temporarily unable to cope. Agriculture responds to intensity changes too. Gentle rain benefits crops. Water infiltrates to roots. Little is wasted. Intense rain runs off fields, eroding soil, carrying nutrients away, sometimes physically damaging plants. Too intense rain can be almost as bad for crops as drought, even if total rainfall is adequate. More intensity also means longer dry periods between storms. This is the flip side. If rain comes in concentrated bursts, there are longer gaps when no rain falls. Even if annual total rainfall doesn't change much, the distribution changes from frequent small rains to occasional large ones. Dry periods between storms stress plants, deplete soil moisture, reduce stream flow between storms. The combination intense rain followed by extended dry periods creates a whiplash effect. Too much water, then too little, then too much again. Systems adapted to moderate, steady conditions struggle with this variability. Natural ecosystems can sometimes adapt, but human systems, agriculture, urban infrastructure, water supply, are designed for specific input patterns and don't respond well to increased variability. This is why average annual rainfall isn't the most important metric anymore. What matters increasingly is rainfall distribution, how it is spread through time, how intense individual events are, how long dry periods last between events. A place might have the same annual rainfall average as it had historically, but if that rainfall now comes in 3 intense storms instead of 20 moderate ones, the hydrology has changed fundamentally, even though the total is unchanged. More intense is what climate change looks like at the local scale. Not necessarily hotter or wetter or drier in simple terms, but more variable, more extreme, less predictable. Weather that pushes closer to the edges of what systems can handle. The changes in rainfall aren't the end of the story. Systems adapt, people adapt, ecosystems adapt. Not all adaptations are successful, not all happen fast enough, but adaptation is happening at multiple scales. attempts to cope with shifting rain patterns rather than simply suffering their effects. Agriculture is adapting through multiple strategies. Farmers are shifting crop varieties, choosing drought-tolerant varieties in areas where dry periods are extending, switching to crops that mature faster to avoid late-season drought. Irrigation is being expanded, where possible, though groundwater depletion is often the result. Conservation tillage, leaving crop residue on fields, helps soil absorb intense rain better and retain moisture during dry periods. Some areas are experimenting with new crops entirely. Regions that were too wet for certain crops might now be suitable. Regions that were marginal for warm season crops might now have reliably long enough growing seasons. Wine grapes are being grown further north than historically possible. This adaptation is opportunistic, taking advantage of changes rather than just defending against them. Urban areas are building green infrastructure to handle more intense rain. Rain gardens, bioswales, permeable pavement systems designed to slow runoff and allow infiltration rather than just channeling water away as fast as possible. These distributed systems can absorb intense rain better than traditional pipe-based drainage. Cities are creating parks that double as temporary detention basins during extreme storms, storing water temporarily to prevent flooding, releasing it gradually afterward. Water management is becoming more sophisticated. Reservoirs are being operated differently, maintaining more capacity for flood control during intense rain periods while still storing enough for drought periods. Aquifer recharge programs are being expanded, capturing high flows during intense storms and deliberately infiltrating that water to recharge groundwater rather than letting it run off to the ocean. Ecosystems are adapting too, though more slowly. Species distributions are shifting, plants and animals moving to areas where rainfall patterns remain within their tolerance ranges. Some species are being lost from areas where conditions change too much. Other species are expanding into newly suitable areas. The pace of change is often faster than ecosystem adaptation, creating lag effects and mismatches. But adaptation is occurring. Some traditional practices are being revived. Indigenous water harvesting techniques, check dams, terracing, traditional reservoir systems are being studied and sometimes re-implemented because they were designed for variable rainfall regimes. Modern irrigation efficiency is improving. Drip systems instead of flood irrigation. Soil moisture sensors precision application. There is innovation in forecasting. Better seasonal forecasts help farmers and water managers plan for expected conditions months ahead. Improved short-term forecasts help cities prepare for extreme storms. Monitoring networks are expanding, providing better data on how changes are actually occurring. The key insight is that adaptation isn't optional. It is happening whether planned or reactive. The question is whether adaptation keeps pace with change, whether it is equitable. Rich countries can afford more adaptation than poor countries, whether it is sustainable. Using groundwater to adapt to reduced rainfall isn't sustainable if aquifers deplete. But the changes aren't beyond human capacity to adapt to, at least not yet. They're stressful, costly, sometimes disruptive, but they're not impossible to cope with. Rain still falls. Life continues. Systems adjust. The future isn't apocalyptic, it is just more challenging, requiring more active management, less able to rely on historical patterns continuing unchanged. Amid all the change, some things remain fundamentally constant. The water cycle itself continues. Water still evaporates, still condenses, still falls, still flows back to oceans. The basic process hasn't changed, can't change without changing the nature of water itself. The physics remains the same. Gravity still pulls raindrops downward. Terminal velocity is still determined by air resistance and drop size. Surface tension still shapes droplets. Condensation still requires cooling air to its dew point. Evaporation still requires energy input from the sun. These physical processes are unchanging regardless of climate shifts. The total amount of water on Earth is essentially constant. Water isn't being created or destroyed, it is just moving through the cycle at different rates or accumulating temporarily in different places. The ocean's volume varies slightly with ice sheets growing or melting, but the total water remains the same. Every drop falling today has fallen before, countless times, will fall again countless times more. The sun drives the water cycle, providing energy for evaporation, creating temperature gradients that drive air circulation. This will continue as long as the sun shines billions of years more. The fundamental engine of the cycle is constant, even if the details of how energy flows through the system are changing. Rain's essential role in ecosystems remains unchanged. Plants still need water, soil formation still requires water, rivers still flow because rain falls. These dependencies are fundamental to how terrestrial life works. They existed before climate change and will persist through it. The amount or pattern might shift, but the necessity remains. The ancient nature of the cycle provides perspective. Water has been cycling for 4 billion years. Climate has changed dramatically many times. Ice ages, warm periods, different continental configurations, different atmospheric compositions. Through all of it, the cycle continued. Rain fell, even if different amounts fell in different places. This isn't meant to minimize current changes. They're real and significant. But it provides context. The cycle is robust. It doesn't break easily. It adapts to changing boundary conditions, finding new patterns, new distributions, but continuing to function. Water still rises, condenses, falls, returns. The dance continues even if the music changes. For someone listening to rain on a window, the constancy matters. The sound is the same sound humans have heard for thousands of years. The comfort is the same comfort. The drop's journey from ocean to cloud to ground follows the same path it is always followed. Individual rainstorms happen now as they've always happened. Clouds form, drops grow, rain falls. One storm, much like storms that fell when your grandparents were young, when civilizations rose and fell, when humans first listened to rain and felt comforted. The cycle is larger than climate change. It preceded it, will outlast it. This isn't reassurance that everything will be fine. Local changes are disruptive and sometimes devastating. But it is recognition that rain itself isn't fragile. The cycle is fundamental to how this planet works. It bent under ice ages and recovered. It will bend under current changes and continue. The water will keep cycling. Rain will keep falling. Perhaps differently, but persistently, inevitably, anciently. Rain has always meant something to humans beyond just water falling. Every culture that has ever existed has related to rain, depended on it, worried about it, celebrated it, feared it, tried to control it, incorporated it into stories and rituals and religious practices. In agricultural societies, rain was literally survival. Crops needed rain at specific times. Too early, too late, too little, too much. All spelled disaster, so rain became sacred. Nearly every ancient religion had rain deities, or rain-bringing rituals. Rain dances weren't quaint superstitions. They were desperate attempts to control the most important variable in survival. If gods controlled rain, then maybe gods could be persuaded, bargained with, honored into providing. Some cultures saw rain as blessing. In arid regions, rain was the greatest gift, the thing that distinguished feast years from famine years. Desert peoples celebrated rain's arrival, attributed good fortune to it, incorporated rain metaphors into their concept of divine favor. Rain meant life, abundance, prosperity. Other cultures saw rain differently. In very wet regions, rain could be oppressive, constant, limiting activity, causing flooding, promoting disease. Mythology in these areas sometimes portrayed rain as something to be endured, appeased, asked to stop. Too much rain had its own devastation. Rain became metaphor, cleansing rain washing away sins or troubles. Nourishing rain enabling growth of new ideas or movements. Violent rain representing divine anger. Gentle rain representing grace or peace. Rain's versatility as symbol is remarkable. It can represent almost any emotional or spiritual state, depending on context and culture. Literature and art have explored rain endlessly. Rain as setting for melancholy reflection. Rain as dramatic element in climactic scenes. Rain as background establishing mood. Rain as character itself. Present, influencing events, shaping outcomes. How many novels or films have crucial scenes set in rain? How many songs mention rain as emotional parallel? Modern cultures maintain relationships with rain, though mediated by technology. We forecast rain, prepare for it, sometimes complain about it, but rarely fear it the way ancient peoples did. We've insulated ourselves with infrastructure, roofs, drainage, irrigation. That makes us less immediately vulnerable, but the relationship persists. We still feel emotional responses to rain. Comfort at hearing it at night, disappointment when it ruins plans, relief when it ends drought. Regional identities are partly defined by rain. Pacific Northwest's identity includes its drizzle. British identity includes its gloomy rain. Desert Southwest's identity includes its dramatic storms and usual dryness. These aren't just weather facts, they're part of cultural character, how places and their people understand themselves. Rain remains culturally significant even in a technological age. We still pray for rain during droughts. We still celebrate rain's arrival in dry places. We still use rain metaphorically in speech and song. The ancient relationship between humans and rain hasn't disappeared, despite modern technology. It is just adapted, continuing in forms that recognize rain's essential role in life's possibility, in agriculture's success, in Earth's character as a water world where rain is the mechanism connecting ocean to land, completing the cycle, keeping everything green and flowing and alive. Why does rain soothe? Why do so many people sleep better to rain sounds? Why is there a comfort, almost universal, in lying safe indoors while rain falls outside? The psychology of rain's comfort is worth understanding. Partly it is acoustic. Rain produces pink noise, a sound frequency spectrum that masks other noises without being jarring. It covers disturbing sounds, traffic, voices, random thuds. With a consistent acoustic blanket, your brain can relax against rain sound, the way your body relaxes against a mattress. There is no spike to startle you, no unpredictable element, just steady, reliable sound that fills the auditory space without demanding attention. Partly, it is evolutionary. Rain meant safety for our ancestors. Predators would shelter. Tracks would wash away. Hunting would pause. Rain created intervals when humans could rest without vigilance, when the landscape's dangers were temporarily suspended. Some deep part of our nervous system still recognizes this. Rain equals temporary safety, permission to let guard down, opportunity to sleep without constant alertness. Partly, it is sensory deprivation. Rain reduces the visual range. You can't see as far through rain. It dulls sounds from distance. It creates a smaller perceptual bubble, bringing the world inward, making everything more intimate. This reduction of sensory input is calming. There is less to process, less to be aware of, less to respond to. The mind can rest because there is less demand on it. Partly, it is the contrast between outside and inside. Rain emphasizes shelter. You're dry, warm, protected. The barrier between you and the weather wall, window, roof is doing its job. There is a primal satisfaction in shelter, working as intended, in the contrast between wet-cold outside and dry-warm inside. This is ancient comfort shelter functioning, protection provided, security felt. There is also the association with childhood. Many people's earliest memories include rain being held while rain drummed on the roof, playing indoors while rain fell outside, that specific coziness of rainy days. These associations, formed when young, persist throughout life. Rain subconsciously recalls being cared for, being safe, being small in a world where someone else handled the concerns. Negative ions might play a role. Air after rain contains more negative ions, molecules with extra electrons, produced by rain's interaction with air and surfaces. Some research suggests negative ions improve mood and reduce stress, though the effect is subtle and debated. But people consistently report feeling better in air after rain, that cleaned, freshened quality that is partly smell and possibly partly ion concentration. The smell of rain petrichor is inherently pleasant to most humans. It is a combination of plant oils released by rain and geosmin from soil bacteria. This smell might be connected to rain's importance in our evolutionary past, associating rain's smell with the greening and food availability that followed rain, creating positive associations that persist as pleasure in the scent. Rain's comfort is multicausal, not one thing but several, reinforcing each other, creating that specific feeling of restfulness and safety. The sound, the shelter contrast, the childhood memories, the reduced sensory input, possibly the ions and scent, all combine into rain's particular comfort. The reason people seek out rain sounds for sleep. The reason rain on a roof creates such specific peaceful contentment. Rain's symbolic richness is remarkable. Few natural phenomena serve as metaphor for such diverse human experiences. Rain can represent almost anything, depending on context, blessing or curse, cleansing or destruction, gentleness or violence, predictability or chaos. Cleansing is rain's most common metaphor. Wash away sins, rain's purification, washed clean. The association between rain and moral or spiritual cleansing is ancient and cross-cultural. Water removes dirt. Metaphorically, rain removes wrongdoing or bad fortune. This metaphor appears in religious rituals, in literature, in everyday speech about starting fresh. Nourishment is another standard rain metaphor. Rain enables growth. So metaphorically, it represents whatever enables ideas or movements or individuals to grow. Raining down blessings, let it rain success, nurturing rain of encouragement. All use rain to represent supportive input that enables development. Sadness links to rain frequently. Pathetic fallacy in literature, the weather reflecting characters' emotions, often uses rain for melancholy. Tears like rain, weeping skies, gloomy as a rainy day. Rain's grey quality, its dampness, its limitation of activity, all map onto depressive emotional states. This isn't universal. Not all cultures see rain as sad, but it is common enough to be recognizable. Abundance and scarcity both use rain metaphorically. Raining money, raining opportunities, rain as symbol of plentiful availability, but also not a cloud in the sky, meaning no relief coming. Thirsty for good news, using rain's absence as metaphor for lack. Violence appears in rain metaphor too, raining blows, storm of criticism, weathering attacks, using rain's capacity for intensity and overwhelming force to describe conflict or assault. Storm metaphors are particularly common for chaos, unpredictability, danger. Inevitability sometimes appears. Rain must fall. Weather the storm. Ride out the rain. Using rain's unstoppability to represent unavoidable difficulties or phases that must be endured until they pass naturally. Renewal and fresh starts use rain constantly. Spring rain bringing new life. Rain after drought representing hope fulfilled. Rainbow after the rain meaning good following bad. Rain's association with growth and greening makes it perfect metaphor for beginning again, for recovery, for improvement following hardship. The versatility comes from rain's multiple characteristics. It is common yet dramatic, essential yet sometimes destructive, gentle yet sometimes violent, predictable in season yet unpredictable in timing, welcome yet sometimes unwelcome. This multiplicity makes rain useful for representing almost any human experience that shares these dualities. Poetry and song use rain constantly, often without much analysis. It just works symbolically. Readers see listeners understand rain metaphors instinctively. Don't need them explained. Feel the emotional resonance. Rain means something beyond just precipitation. It carries symbolic weight that other weather doesn't quite match. Snow is beautiful but limited metaphorically. Wind is powerful but abstract. Sun is positive but simple. Rain is complex enough to carry complex meanings. This metaphorical richness is part of rain's cultural presence. Rain isn't just weather. It is a symbolic language, a way to talk about life's complexities, a metaphor that everyone understands because everyone has experienced rain and knows intuitively what it can represent. The sound that helps you sleep is the same sound that has provided symbolic meaning for countless generations, that has represented human experiences across all cultures, that remains metaphorically resonant because rain itself remains essential and ever-present. Here is a strange truth. You are rain, not metaphorically, literally. The water in your body right now was rain once. Probably many times. The water you drank this morning, the water in your cells, the water in your blood, all of it was rain at some point, possibly multiple points. In its long history, water doesn't get destroyed. The water molecule that is currently in your body has existed for billions of years. It has been ocean water, ice, cloud, rain, groundwater, river water, plant sap, animal blood, possibly other humans, bodies, definitely rain numerous times. That same molecule will exist after you die, will be rain again, will cycle through the system countless more times. About 60% of an adult human body is water. That is roughly 10 gallons for an average-sized person. All of it came from outside, drinking, eating food that contains water, even breathing in humid air, and all of it will leave urine, sweat, breath, tears. You are a temporary collection of water molecules borrowed from the cycle, used briefly, returned to the cycle to continue their endless circulation. The water you drink was likely rain fairly recently, days to years ago, depending on whether it came from surface water or groundwater. If you drink from a river, that water was probably rain, weeks or months ago. If from a well tapping deep aquifer, possibly centuries ago. Either way, it was rain before it was your drinking water, and it will be rain again after it leaves your body and re-enters the cycle. This means you are connected to the entire water cycle. The cloud you see isn't tea separate from you. It is potential you, water that might become yours through drinking. The rain falling outside will eventually be drunk by someone, somewhere, becoming part of their body temporarily. The water you excrete will eventually evaporate or flow to ocean, evaporate there, form clouds, fall as rain, possibly be drunk by someone else, becoming part of them. This isn't tea mystical. It is straightforward material science. Molecules cycle, water cycles. You are part of that cycle, a temporary node in the network, a participant in the ancient exchange of water between ocean and atmosphere and land and life. Indigenous cultures often recognized this explicitly. Water is sacred, not because it is supernatural, but because it is connection. Connection between all life, all places, all times. The water in the river is your water. Is there water? Is everyone's water? Is the same water that nourished ancestors and will nourish descendants. This recognition creates respect, care, understanding that water isn't tea resource to be owned, but commons to be shared, cycle to be maintained. Modern cultures often miss this. We treat water as commodity, as something separate from us, as resource to use. But the science is clear: we are water, temporarily organized in human form, completely dependent on water, continued cycling, inseparable from the hydrological system that includes rain and rivers and oceans and clouds. Next time you drink water, consider its journey to you. It was rain once, possibly recently. It was ocean before that. It has been cycling for billions of years and will cycle billions more. You are just borrowing it, using it briefly, then returning it to the eternal circulation. You are part of the cycle. You are rain. We've come far from where we started, from the simple sound of rain on your window through clouds and condensation and the entire cycle. But now let's return to that beginning, the raindrop on the glass, the sound that helps you sleep, the comfort of rain falling while you rest safe and warm. You understand it differently now. That drop wasn't always a drop. Days or weeks ago, it was ocean water. Then vapor, then cloud droplet, then raindrop falling, arriving at your window as the conclusion of a long journey, and soon it will begin another journey, evaporating or running off, eventually returning to ocean or soil, eventually rising again as vapor, eventually condensing into another cloud, eventually falling as rain again. Humans have been listening to rain for as long as humans existed, hundreds of thousands of years. Your ancestors heard this same sound, felt this same comfort. The physics hasn't changed. Drops striking surfaces create percussion, create rhythm, create that sound that allows your mind to settle, your thoughts to slow, your body to relax into sleep. The cycle continues regardless of your attention to it. Rain will fall whether you're awake to hear it or asleep. Clouds will form whether you're watching or not. The sun will evaporate water, air will rise, cooling will cause condensation. Drops will grow and fall over and over, endlessly, as long as the sun shines and the planet holds liquid water. Your understanding of rain doesn't change rain, but it might change your relationship with it. Knowing that the drop contains molecules billions of years old, that it traveled from ocean to cloud to window, that it is part of a cycle that predates humanity and will outlast it. This knowledge can deepen the comfort. You're not just hearing rain, you're hearing an ancient process, a fundamental characteristic of Earth as a water world, a sound that connects you to the entire planet's hydrological system. The journey we've taken, from window to cloud to vapor to ocean and back, is the journey every drop takes, endlessly varied in specifics, but consistent in pattern. Rain is both utterly common and profoundly remarkable. It is everyday weather and cosmic process. It is background sound and essential phenomenon. It is simple falling water and complex journey through phase changes and geography and time. Tonight, rain falls somewhere, maybe on your window, maybe elsewhere, but somewhere, the cycle continues. Evaporation, condensation, precipitation, collection, solar energy driving water from ocean to atmosphere to land and back. The same process that has occurred for billions of years, that created oceans, that enabled life, that sculpted continents, that makes Earth the living water world it is. And somehow, despite all this complexity, despite the science and scale and ancient continuity, rain remains comforting. The sound still soothes. The knowledge doesn't diminish the comfort. It might even deepen it, connecting you to something vast and ancient and ongoing, something that preceded you and will continue after you, something you're part of, even while listening from bed, something as simple as water, falling, and as complex as planetary systems, cycling matter, and energy through endless transformations. The rain continues outside. You've followed one drop's entire journey, but now there is nowhere left to follow. The story has come full circle. Water from ocean to cloud to rain to earth, and eventually back to ocean to begin again. The cycle is complete. Or rather, it is never complete. It just continues, each ending being another beginning. Your thoughts are slowing. This is natural. The rain sound supports this, that consistent acoustic presence that allows your mind to stop searching for meaning in silence, to stop being alert for unexpected sounds, to just rest against the steady rhythm like resting against a pillow. Your breathing has probably changed while you've been listening, slower, deeper, more regular. This happens naturally with rain sounds, with relaxation, with the approach of sleep. Each breath is its own tiny cycle, air in, air out, oxygen and carbon dioxide exchanged. Your body participating in chemical cycles just as it participates in water cycles. Let the images from this journey drift through your mind without holding on to them. The cloud, the drop forming, the long fall, the window, let them float like the droplets themselves, drifting, merging, dissolving into each other, and into the general sense of water moving, cycling, falling. You don't need to remember any of this. The facts, the mechanisms, the science, they're interesting, but you don't need to retain them. Let them go. Let them evaporate like water from a surface, rising invisible into the air, becoming part of the general atmosphere of understanding, without being discrete pieces you need to hold. The rain itself doesn't require your attention. It falls whether you're listening or not. The cycle continues without your awareness. You can let go of focus now. You can stop following the water's journey. You can just hear the sound without thinking about what it means or where it came from. Just sound, just rhythm, just rain. Your body is heavy. This is good. Heaviness means relaxation, muscles releasing tension, settling into whatever supports them. Like the raindrop finally reaching the ground, you're reaching rest, completing your own daily cycle of activity and sleep, finding your own conclusion that is also a beginning of rest and renewal. The window can hold the rain. You don't need to. The sound can continue without you listening actively. The cycle can proceed without you understanding it. Everything will continue, rain falling, water cycling, the world doing what it has always done, whether you're awake to witness it or asleep. Let sleep come like rain comes, inevitably naturally, without force or resistance. Let consciousness drift like vapor, diffuse into the surrounding quiet, dissolve into the sound of water falling on glass. You're safe, you're sheltered. The rain is outside, you're inside, and sleep is approaching like a raindrop, falling toward earth, slow, steady, inevitable, welcome. The sound continues. The rain continues. The cycle continues. And you, listening, drifting, can let go now, can sleep, can rest. The story is complete. The circle is closed. The rain falls. And you, falling gently into sleep, are part of the same ancient rhythm, the same patient cycle, the same return to rest that water makes every time it falls to earth and pauses before rising again.